Hello there, thank you for joining me again today. On the bench is a Kenwood TS2000 ham radio transceiver. This particular radio is a HF, VHF and UHF all-mode multibander TS2000 model radio. As I say, this does all radio frequency bands really, and it's even got a 23 SEMS which is 1.2 to 1.3 gigahertz option that you can have fitted, which goes in the side here, which we'll look at. But this has come to me with a fault on it of no TX output power on HF bands and 2 meter emitter band, which is 144 megahertz, 145 up to 147. So we're going to have a look at that and just confirm all these faults using the IFR 2968 radio test set. Now, according to the information that I've got, this radio transceiver does work on receive on all frequencies, but not on transmit. It only transmits on UHF correctly. All the other frequency bands it doesn't. Now, we've got it on UHF at the moment, but I just want to show you, if I press this sub key here, then we've got it on 145. Then it drops down to 52 megahertz, which is a 6 meter emitter band, 51 megahertz, 50 megahertz, because I've got it in 1 megahertz increments. Then it drops to 29 megahertz because it goes right up to 30 megahertz and above, because we've got predetermined band splits. So basically it goes right from 0 to 50-60 megahertz roughly on the HF band, and obviously each time I select I'll put megahertz key there. That's 50 megahertz right up to 52, goes beyond right up to 57, 58, 59, 60. So it's basically 0 to 60 megahertz. So basically from 50, I think it was 50 kilohertz or 30 kilohertz right the way up to 60 megahertz. So it covers a complete HF band and into the VHF low band. So apparently that doesn't work in any mode on transmit, but it does on receive. And obviously then we've got all the different bands as well inside. We can select through the predetermined ham bands, and then it gets back to 433, VHF again 52, and then right the way down. Now this transceiver does all modes as well. It does AM, FM, does CW mode, lower sideband, upper sideband as well, on all frequencies, so it's not limited in frequency range to what mode it operates in. It's a fully featured radio with digital signal processing, many features on it, that is extremely complicated radio. It also does satellites as well, so that you can select VHF and UHF at the same time, so your uplink and your downlink. So it does that, and you can change all your splits, program it for repeaters, scanning. It has a variable output power on transmit, so we can select from a minimum of 5 watts right the way up to, in this case, in 5 watt steps up to 100 watts. And on UHF the power again can go up to 100 watts as well, so right from 5 watts to 100 watts, and the same on all the other bands. So it's actually quite a as I say, a fully featured radio transceiver. So we're going to have a look at this. We're going to do some tests and measurements just to see what the fault is and confirm it before we do anything. And then we'll look inside the radio and look at the circuit information and the service manual that I've got, and take it from there. I think it'll be a good video. You'll enjoy it. So onwards and upwards. Okay, so this is the back of the radio now, and what we've got is multiple antenna sockets for the different bands. So we've basically got here the 144 megahertz VHF output. Then we've got the UHF input output, and then we've got here two HF antenna connections that we can switch between these two ports if we want dual antenna working. But basically this is the 0 to sort of 60 megahertz connection there for input output. And we've got the DC power. I think this is for an option that's fitted externally, and then we've quite a lot of other things as well. We've got all kinds of options that we can plug in these ports. I think there's some optical fibre connections as well somewhere on it. AF in out, RCAs for recording of audio signals and things if we wish to record what we're listening to on the radio. And there's quite a lot of accessory connections. We've got a serial port here as well, which is for external peripherals, I believe, and COM port, so to work with software and things like that, and then external earphone and speaker connection as well. So that's what we've got round the back of it. This is where the 23 SEMS emitter band module would fit. It's not fitted on this one, but basically it's an option that you can purchase and then install it into this cavity here. And I think it uses a Mitsubishi brick, because that's what this surface is for the RF power amplifier. One of the Mitsubishi RF hybrid modules that does the transmitting. So yeah, that'd be interesting to acquire that at some stage. And looks like we're joined by the technical manager. Might make an appearance very shortly on the bench. But there's quite a bit to this radio, obviously. So we'll just get the test set going now and do some measurements. Okay, we'll just set the radio up now onto UHF. I've selected a power of just 5 watts. You can obviously adjust it right up to 100 watts, but I've just left it at 5 watts on low power. And just looking at the current consumption, we're using this power supply down here that can only deliver 15 amps, but it's drawing 2.27 amps at 13.8 volts DC. So that's its sort of quiescent current operating at. So what we'll do now, we'll just turn the split off so we know what we're dealing with, just that frequency there. Okay, so what I'm going to do now is I've got the aerial connection at the back plugged into the Marconi test set, so we'll just check to see what's going on, and I'll just show you on the screen here the measurement. So I'm going to key the microphone up now, and which I'm doing. 1 2 3 4 5 5 4 3 2 1. So the modulation, the FM deviation, 4.5 5 kilohertz roughly. 5 1 2 3 4 5 5 5. So the modulation's good on FM. We're doing obviously in the top right 5 watts, and the frequency that we should be transmitting on is 433.5 megahertz. So that seems to be okay, very close, only just a fraction of frequency. Now I'm going to adjust the RF power level. Now we're doing 10 watts according to the front of the radio, and we're just under that on the test set. And then right now we're on to 15 watts, 20 watts, 25, 30, 35, 40, 45, 50. It's drawing 12.5 amps on the ammeter on the power supply. So 50 watts maximum is what it will do on UHF. Even though the control earlier when it was in receive mode went up to 100, it can only do 50 watts on UHF. So there we are, 50 watts, so it's doing quite well. Everything seems to be working as far as on UHF on transmit. Now I'm going to try some of the other modes in a moment, but I'll just keep it on FM just for the time being. So what we'll do now, we'll set the RX test up. We'll do RF frequency 433.5 megahertz. We can see there we've got a level coming through, only modulating at 2.5 kilohertz deviation. So we'll just test the receiver sensitivity now and see how good that is. And some dBm, it's pretty good there, very sensitive, but it squelches out. So in microvolt terms, I can get the display to show us microvolts. There we are, sort of 0.1 microvolt, or it squelches out. That's pretty good, nothing wrong with that. Of course we could go to AM mode and then check that on the same frequency, so I could do, I think it's mod gen level, and then put in something like 60% modulation, which I think is there. There we are. So that's AM now on UHF, and again that seems to be working okay. Yeah, that seems to be okay. Then we could do SSB modes as well, so we're going to RF test on here, I think it is. Hang on, wrong one, RF test. SSB modes, I think is under... now then, where was that? Oh, that's AF, sorry. Right, here we are, look. Full function multimeter, How did I select it now? I think that's it. RF single sideband SSB mode, there we are, look. So I'll select RX SSB. I'll just move the mode now to SSB, upper sideband, lower sideband. And let's have a look. Yes, we're on LSB, which is up in the top left hand corner there, and we're receiving that. So that's it there, 1 kilohertz. So we'll change it now to upper sideband, and then we'll alter this now to upper sideband. So that all seems to function, and so there, it's pretty good. No problem with upper sideband or lower sideband. So I'm happy with that. So UHF seems to work. So I think what we'll do now, we'll just switch to VHF 145/500, and we will just connect up round the back the VHF antenna, which is on the top corner here. And we'll just move that radio back into position. Right, what we need to do now is effectively repeat that. So it's got an FM mode at the moment, the RF power set to 5 watts. So what I want to do is just go back up to this test set. I just want to be able to set it up. So just have a look, see if we can set it up. So we've got it in SSB mode again. Could always try it in SSB mode first, that might be the best thing to do actually. Let's have a look. RF frequency 145.5, and then the megahertz key. Now we're on, let's put it on, that's upper sideband. And we're on upper sideband on this top corner. Oh dear now, RF gen level. There we are. That's okay. Go to lower sideband. Again, no problem there. We're receiving a signal, that's good. So if I now go to TX test, and now I'm going to see whether, oh hang on, and then we go on here, SSB TX. Right, we're on the 145.5 megahertz frequency, so I've set the power to 5 watts, so I'm going to key up on the radio now. And 5, 4, 3, 2, 1, 1, 2, 3, 4, 5, 5, 5. So there's nothing there, there's no carrier there at all. Now if I go to the spectrum analyzer just to confirm, see if there's anything there, and there's nothing there. So that's not picking anything up. So yes, I think that's looking like as if the RF power amplifier is dead now. It's when I unkey the radio. We'll just have a look at the power supply for a moment. When the radio is in RX mode, it's drawing 2.1 amps, and when we're transmitting even at 5 watts, it's drawing 3.4 amps. So there's something working, obviously. Probably one of the exciter amplifiers or the preamp before the RFPA is probably working, one of the early stages. It's drawing current, and even if I change the RF power on here up to say 30 odd watts, if I press to transmit, the current isn't changing no matter what RF power. So obviously the RFPA stage isn't working. So that explains that. Now that doesn't matter whether I'm in sideband mode at the moment. I'm modulating the microphone as I'm talking now, and as you can see the current isn't varying. And if I just put that into FM mode and transmit again, same amount of current no matter what. So yeah, so that looks like as if the RFPA isn't working on that. Now we've got it in FM mode now, so what I need to do is I just need to set up this test set to display FM mode. So let's just have a look at doing that now and see what we can do. That creaky noise you can hear is my knees. Right, so how do we come out of sideband test now? That'll be interesting. SSB single output, blah blah blah. I think I might just reset the test set actually, because it'll probably be easier. Just press the reset and then should just come up with it. And then we can go back to right, RX test, HF frequency, 145.5 megahertz. So we're receiving a signal. Again, we're only modulating it with 2.5 kilohertz deviation level. Test the receiver sensitivity. Nothing wrong with that. Again on AM. Put it to AM. Set mod. RF gen. Set mod level. RF gen level. Set mod gen. That's it. Level. 60%. There you are. So that's working. So that proves SSB, AM, FM and low sideband, upper sideband's not working on transmit on the VHF, but it is working obviously on receive. So that proves that. Okay, so now then, we just moved it from 145.5 down to 52 megahertz. So this means we have to move a connection at the back to the HF connection on the rear. So we'll just do that now. And just take that off there, put that onto the HF connection. If it'll go on. There we are. Right, so 52 megahertz. We'll go to TX test and we'll just leave it in auto tune mode and we'll just see whether we can get any output power. Leave it at 5 watts. There's nothing coming up at all on the Marconi. No indication there at all. That's in receive mode now, transmit mode. So if we go to duplex, RF gen frequency, I'll set this up now as 52 megahertz direct. I'll put it on FM. So we'll put in now 52 megahertz. RF gen level. Change the mod gen level back to 2.5 kilohertz. RF gen level. Nothing wrong with that. It's receiving good. Okay. But unfortunately, it ain't transmitting. So, if I TX now, you see, not picking anything up at all. There's nothing there. Now if I go on to TX and then spectrum analyzer, there's nothing there at all. Did I select the right one? Spectrum analyzer, there we are. So it's in receive mode, that's in transmit. On transmit it's only drawing 3.4 amps. So again, same fault really. Okay. So I've changed it now to 50 megahertz dead. So I don't think we're going to see anything. Yeah, on transmit it's not picking anything up. 29 megahertz now. Transmit. Nothing coming through. It's not auto tuning. So we'll just check the receiver. The RF gen frequency. 29 megahertz. That's okay. So that's receiving. I'll just go down now. 28 megs, 24, 21, 18 megahertz, 14 megahertz. So I'll try it at 14 megahertz. 4 megahertz. Put it onto FM. And then I've done that right. Level. Yeah, nothing wrong with that. But under TX, of course, if I key up, nothing. Absolutely nothing. Again, same current draw, 3.53 amps. So again, this is what we're getting. So on 14 megahertz on transmit, 3.4 amps on transmit and 2.44 on receive. So something's working, but so receiver's working fine on the radio, no problem at all. But of course there's obviously something wrong with the transmitter amplifier stage. So we'll have a look inside the radio now and have a look at the schematic diagrams. Okay, so we've got the radio on its side now, and this is the entire RF amplifier output stage for the VHF, which is these two transistors, and then HF, which is these two transistors. Now over on the far right here we've got two coaxial inputs that come in, one with a black band and one with a yellow band, one of which carries the 144 VHF megahertz range to this amplifier, and then the other one carries the HF range, the 0 to 60 megahertz, which is then sent to this amplifier. And I can't see these output transistors being blown, because if that was the case we would more than likely, if one transistor of each failed, be getting a different fault symptom, i.e. low output power on transmit, but you know, there'd be something there. Whereas in this case neither HF, which is these two, or VHF, which is these two, are working, and I can't see all four transistors going fizz bang. Of course there are circumstances where that could happen, where there's been a lightning strike, and of course the antenna in the discharge moment of lightning has perhaps given an incredible spike up these transistors. That is possible, you know, it does happen. I've seen that happen before and heard of it happening on other people's radio equipment, but I would have expected damage if that was the case from another input here causing severe damage to the antenna tuning unit, because on this radio this top section here is like an ATU, and so is this bit. This is all an antenna tuning unit, which automatically selects the right inductive and capacitive elements to tune to an external antenna. So it's an automated ATU. Now with this amplifier not working at all on HF and VHF means that I would seriously doubt all four transistors would have failed. We are, however, getting some current draw when we're transmitting, and with the look of a configuration it looks like we've got a balun just here. We've got an RF transformer which appears to be supplying RF to what appears to be these two transistors, which then goes through another transformer on the output of that. These probably provide about 10 watts drive between them, about 5 watts each. These are commonly found on CB radios quite a lot, the 2SC 19 whatever it is 72 transistors. They're then fed into another RF transformer, and then the next RF transformer then couples the RF into these two transistors. We've then got a feedback arrangement, RF feedback. We've got a capacitor and a resistor going between the collector and base, and so thus that they provide some RF gain, some further RF gain by feeding back RF, and then the output of the two power amplifier transistors is fed into this large transformer, and then obviously fed out then to the ATU from this coaxial cable here, with the look of it, to the ATU unit. Same with the VHF side of things. It looks like we've got, when we look at the breakdown here, there's another RF transformer just here which appears to feed an RF signal path in this direction, which then comes into this what looks to be a if that's in the RF path, I seriously doubt it, but I think that's for biasing. Again, looks like as if we've got some amplification, pre-amplification. We've got capacitive inductive matching to each RF transistor. It looks to be a Wilkinson combiner because we've got the resistor here for balance. then enters both transistors. Looks like we've got a temperature compensation diode with some heatsink compound over the shell of this transistor, the output of which then is again in like a Wilkinson mode, where we've got large power resistor, inductive elements, strip line where the signal combines together. These obviously tuned to like quarter wave resonances, and then the output then is fed down this track to this connector, and then it enters the ATU. So there's obviously something going on here, I think. Now the UHF board is on the other side, sandwiched between the control board and the chassis bottom. So it's a similar board to this in appearance, but it's only obviously half as wide because it's only got the transistors on for UHF. But that's working, so we don't need to look at that really. So I think it's now time to look at the diagram and see how it works. It could be there's a supply issue. I would doubt it in this case, because the main supply from the rear connector is actually connected directly to the board on these points here, and therefore the whole supply is there. They mainly are unfused at this stage and go straight through RFC radio frequency chokes to the collectors of all the power transistors. So I can't see there being a supply loss, but you never know. If it's relay controlled or something like that and it's not connecting power, so that's something we need to look out for. It could be that one of the driver transistors, it looks to me with the way it's configured, we've got two RF power transistors here and then a pre-driver, and that pre-driver could not only deal with the HF frequency band but also the VHF, and so therefore this transistor could feed both amplifiers, and also then of course these two are just for this HF side. Likewise we've got I think a preamp in this area here, which then drives these two RF power transistors, and the balance is set via these two capacitors. There are transistors here that also supply bias to these transistors for AM and SSB modes, obviously for the changing the class of the amplifier, because obviously when we're using it in FM mode it'll be a class C, but when we're using it in AM or SSB modes it'll be a class AB, because they'll be given bias, and you can set those biases up with potentiometers, which I can see on the board in various places. So you know, there's a potentiometer there for example as well, and there's a potentiometer there, that orange top one, which will set the bias in. So there's some good indications here. So we'll have a look now at the circuit diagram. Right, so managed to search through the service manual, which is quite a well written in-depth manual, and this is the RF amplifier section that we'll just be looking at on that board. Now I'm just going to zoom in a little so we can see a bit more detail here, and pardon my knees. Right, so on the edge here, these two are coaxial inputs, which if you remember when we're looking at the board itself, was two coaxial cables, and it signifies here, one of them says, I think it says, is it HF or something, or 140 something, 14, something like that. It's might be written on this actually. There we are, look. So I think it's sort of tries to explain in a way what's on. So this is a TX unit there that's connected on one coaxial input, and then again another one, and it says HFTX just there, and then this says 140X, which is short for 144 megahertz. So both HF and VHF inputs are fed in to this device, combined obviously on the output, and then we get an amplification by this 2SK. Let's see, just grab it and move it a bit. So we get amplification by this 2SK 2596, FET. RF output's fed on there through this inductor along here, and as if by magic it gets to this 2SC 1971 pre-driver. So that was that singular TO220 device we were looking at on that board. The output again fed through an RF transformer, which we identified on the board, and then we get to what are the two TO220 power transistors which we were talking about with these 2SC 1972s, which are those black square TO220 transistors that we saw mounted together. And the output of that again is fed via this transformer. Obviously in both these cases we've got a DC rail, which is shown in red, which supplies DC power. And interestingly enough, just seeing out my eye corner down here, there's a fuse in that area, F1, so that'd be interesting to find out if that's blown. So yeah, that'd be interesting. But anyway, there's a supply coming in which branches off obviously to feed various parts of the circuit via radio frequency chokes, and again we've got a supply branching off here which then goes round obviously through this transformer to feed the collector on this transistor, and the RF transform takes place across onto the opposite side, and then we're feeding an RF in as a balanced input then to both transistors, these 2SC 1972s, which again are those black transistors. And then we have a DC feed, supply feed into the center tap on this transformer, RF transformer. So this forms an RFC as well as part of its transform function over to the secondary winding. RF appears there, and then we've got some kind of relay here with the look of it. Now I would say, let's say it's surge absorption, so that's obviously something perhaps maybe to do with it. I was just looking at seeing whether I could find where it went to. But then of course we have this RF amplifier at the top. Now this is the HF RF amplifier. So if I just move it on a bit after we've just looked at this transformer. So again, the RF output fed through this relay shenanigans, and then basically there's again another signal path down here which then goes into this transformer, and then we leap across, and this is where the balancing takes place. So the balancing then is in this section in the lower half as well as in the top half here. So we've got a balanced RF signal across this 100 ohm resistor matched into each input. In addition to that, looks like we've got some biasing as well, that's switched in and out, probably via that this path here. So this, yeah, temperature compensation. So that potentiometer there, down here, this potentiometer controls the temperature compensation or the biasing. This looks like it's a bias adjust, and this transistor conducts then up to the center tap on this transformer, which then delivers DC bias to both transistors. So then of course we've got the main RF power transistors on the output, final drive. We've got obviously another RF transformer on the output. The supplies on here look like they're derived from this line here. So we've got again the full supply potential through an inductor, then onto what is the center tap of the transformer. And if I just zoom in a bit further, so that's where we've got that supply rail fed down the centre of that large transformer, and then each winding separately then takes a supply off then to the collectors of these power transistors. Likewise, again, we've got a split off again here, so the whole switcher, if you like, the switching of the RF signal takes place in this coil here on the transformer, and it transforms across, and then we've got an output then which goes off to the antenna tuning unit eventually, and that ends up going off right the way along to there. So that explains the HF amplifier. Now if I zoom out again and we have a look earlier again, way back here at this section, which is, let's have a look, see if we can find this. Way back again, right back to this pre-amplifier stage. Now then, comes in there, both inputs, HF VHF again, through that amplifier, through this amplifier, again through these 2SC 1972s, then across to there. I'm just trying to find out how it gets its feed then to the VHF high band amplifier. Ah, there it is, look, I missed it. So after those two 2SC 1972s, this relay here switches a path with the look of it. So HF path gets directed left there and comes down here, obviously into that HF amplifier that we were just discussing. But also if the relay switch the other way, then we get again the VHF 144 megahertz signal, I presume, going this way by this arrow here, and that then connects into this amplifier, yes, which is a 2SC 2694s. So it uses the same preamp for the HF as well as the VHF, which is those two 2SC 1972s. So that basically, if we just look down here again, the amplifier, so that's these two and that one. So these amplify the signal for not just HF but also VHF as well, the VHF 144 megahertz spectrum. So interesting. Okay, so that path comes along there for VHF high band down to here, and then it enters this again type of Wilkinson combiner. Got two capacitors for tuning it, excuse me, inductive capacitive elements. Then it goes into the RF power transistors, which are those two white power transistors, and again it's a very similar thing where again we've combined the outputs of both transistors at this junction, and that then is fed off. Then there's obviously a reflectometer, part of the ALC circuit for detecting the SWR, and then obviously adjusting things as necessary if it sees a high VSWR, and that then goes out. That 1.4 PO is 144 megahertz power output, and then it's actually said 144p in there, and then off it goes then via relay and into this, what is the antenna tuning unit then, which, you know, goes off to that. So yeah, so I think what we need to do, if we go right back to the sort of beginning here, which is this preamp stage, in this area here, we've got obviously this relay switching going on here. We've got the amplifier. I think we're going to have to do some tests round here, but I think the very first test we need to do, if we go right back to basics, is to see whether we've got those signals present here on these sockets. Because if a drive signal for HF and for VHF isn't present at these junctions, then obviously the module beyond this, further than this, these two here, these may be at fault, or they could have a common supply issue, or it could be that we've got a problem in this area, in this section, using these 4 transistors. But I do want to find, before I go any further, this fuse here, which is this baby, and that's called F1, and it's rated at 5 amps. Now, I could just go on to the collectors of these transistors to see whether there's any supply on them as well. That'd be a quick way of doing it. But I just need to find out where fuse 1, 5 amp is. Right, I found out where that fuse is, that little fuse 1. It's quite difficult to spot actually. This fuse here is fuse 2, and that's okay. But the fuse 1 is this little device here. It looks like a resistor. I think it should be one of those circular things. It looks like a mini bridge rectifier with 2 legs on it, but they've put in what looks to be just like a standard, I think it's a 3 amp fuse or whatever it is. It says 5 amp on the diagram, but that's it there. So I just need to get onto that. So what I'm going to do anyway, I'm going to make things a bit easier for myself. I'm just going to connect up a crock lead with the negative side going to the multimeter, which is just sitting behind here. So I'll just connect up that. It's on volts at the moment, DC volts, so I'll just connect that permanently to the chassis on the neg side. And then we've got the probe, if I can get hold of it. This is there. Right. That's that. We're on volts as well. So I just want to be able to see the let's move that out of the way. Right. So now we can sort of use this probe now to go on to various places to see what voltages we've got. So here we go. We'll switch it on, the radio, and there we go, it's switched on. Right, so on to here. First of all, just check, see what supplies we've got. Obviously 13.6 volts there, which is fine, no problem there. We'll just go on to the collector of these transistors just to see what we've got. So again, 13.6 volts on there on that transistor, and let's check this one. This is on obviously on the VHF power amplifier, high band VHF 145 megs band amplifier. That's supplies there. We'll just go on to the HF transistors now for the HF band. Again, just checking those. I've got 13.6 volts on, as we can see in the bottom right hand corner of the screen, and again just with this. Now we can go on to there actually, because that's live. Yeah, that's all there. Okay, so now we'll try and check this fuse as well. Looks like, because I can only get onto one side of it, because obviously the bottom end just disappears under the board, but the top end looks like it then gets supplied to that choke there. So let's just see what we've got there. Doesn't appear to be anything there, just mildly something. Am I not on it properly? No, there's no supply there. So if you have a look at one of those transistors as well, let's have a look here. I think, yeah, I think if we have a look at one of those 2SC transistors, might be able to normally I think on the 2SC 1972s I think the tab is actually the emitter, because that's obviously better for an RF ground, but we'll see. Yeah, I think I'm right there. There's quite a lot on these bipolar transistors that are used for DC. The tab's actually the collector, but I'm just going to go on to one leg first of all. It might not be there until we transmit actually the voltage, but it doesn't show that on the diagram. It's not, there isn't like a transmit voltage. It says RX mode as well, should be 13 volts. So we should be getting a supply. Obviously I don't expect anything on the center leg, because that's obviously the emitter in this case, I think, and then obviously that was something it was trying to read just there, but no, it's not picking anything up. So there's no voltage on that transistor either. So I think we've got an issue with this fuse. Now whether we've got a short circuit, that's something else. So I can test for that now. So what I'll do, I'll just remove the power to the radio so that we don't upset anything. I certainly don't want any DC volts, even though I can't measure anything coming up the voltmeter. So I'm just going to put the DC meter now that we've got here into ohms mode. Just test it on the chassis by shorting out the probe, and we can see there we've got 0 ohm short, which is good. So now I just need to measure on the output of that fuse 1, to see whether we've got a short circuit, because what I don't want to do is replace that fuse if there's a short and then find it blows again. So let's just have a look, and it does look like as if, oh, hang on, that's wrong, 103 ohms, so that's fine. We haven't got a dead short then on the output of that fuse. So where we've just been looking on the diagram, if I just switch that light off so we can see a bit better. On the diagram we've just been looking there on that fuse. So we've just been on both sides of this fuse, well on one side anyway, this top side, and that L6 there is actually that ferrite bead, it looks like, with a solid bit of wire running through it. So we've also been to the transistors as well. So we went to these two transistors to measure the voltages on the collectors, on these two obviously, just in case, because it was a bit tarnished, the connection on that fuse, and sometimes these probes they don't connect very well. So I thought I'd go on directly onto the places just to verify, and there was nothing on the collectors on these transistors, and there should be even in RX. You've got to be careful with these radios as well, because sometimes supplies aren't there on the transmitter side until you transmit, because there's a transmit receive switch. So there'll be literally a relay that will click on power, or a bipolar power transistor that will enable voltage to the amplifier when it's in transmit mode. But on this we can see both receive and transmit voltages on these, the gate of that, obviously on the drain source on that, and then obviously on the collectors on these, they're all there, the supplies, whether it's in transmit or receive mode. So that's a good indication. But it does look like as if we've got a blown fuse there, but we've just measured continuity between this line and chassis to see whether we've got a direct short, as in say one of these components has gone short or something of that ilk, but there's nothing at all indicating anything that would result in a short circuit. So just a bit worried as to why that fuse is gone, what possibly could have occurred to cause that fuse to blow. Is it just a weak fuse? Is it a fault condition that's caused the failure? At the moment, you know, it's not showing as being a short or a near short, so Do I just go ahead and replace that 5 amp fuse and see what happens? There's also another thing I can do as well. I can feed a supply onto it if I wished, and then see how much current it draws using a current limited power supply, because I wouldn't want to replace that, and if a short did happen then a component burn out and cause damage to the board or other components, so that's a possibility. But that fuse only supplies power to these 2SC1972 transistors and this 2SC1971, which are the 3 black square transistors, and also it supplies power to this, albeit via these inductors. Normally if these devices had gone short or something like these caps, sometimes these inductors can burn out depending on what values they are and how thinly the wire is on them, but can't see any signs of burning. There's no burning smells or anything obvious when I was looking at the board that showed any faults. So it might just be one of those things. It might be that you know, it was being used at IPOW, maybe IVSWR something, and it's just blown that fuse. Who knows? But yeah, so we've got a voltage regulator. These voltage regulators also are supplying this main input supply rail there. We've got a relay that's switching the supply across to this line as well. That's obviously a main supply rail. So yeah, a few things here we can go on. I think I'm going to have to look at options around replacing that fuse now. Okay, so just further on this then, I've done a bit of research onto this fuse, which is just here. It's this device just there. You can probably just make it out. Now, these are being sold quite widely on auction sites, these fuses. And I read an article about it being caused, the fuse blowing, through the contaminants of the manufacturing process of chemicals that are used on the board. Now, I'm not aware of that on these, because obviously I've not repaired many of these over the years, but I find that quite interesting, because apparently, according to the information I've read, it blows for no reason, and there must be some, I would have assumed, solder swarf, or perhaps these micro globules that are used as part of the solder rework. So they have little balls of solder, microns in diameter, that are used in a paste, on the solder paste, and as and when the heat's applied to the circuit, when it gets flowed, especially with these power transistors, they will actually short out, perhaps, if they're not cleaned after the soldering's taken place. So I assume that that could be the case. Also, it could be that there was some corrosion from the chemical process of washing the board, but I can't see any evidence of that on here. But apparently this fuse is known for blowing unexpectedly. But that's interesting to know, because I wasn't expecting that. I was sort of expecting a fault, as in I was trying to theorise that there could be either an antenna mismatch because of the ATU circuit, which comprises of all this section on the left and at the rear here, may possibly have driven a high VSWR on the amplifiers when they were in use, and thus reflected higher VSWR, has then made obviously the drive situation worse, and perhaps it's consumed more current because it's trying to drive transistors, which is obviously putting its output, say 100 watts, into a high VSWR, and that will then have a back effect further down the chain, and thus perhaps it may induce further current to be consumed by the other driver transistors, which then could blow the, especially if it's getting to the limits of the fuse, it could then pop the fuse. And I was also theorising, as the reason for doing the continuity test between there and chassis, with chassis neg VE, we were looking to see whether there was a short circuit on the output of the fuse, considering there's numbers of electrolytic capacitors that are situated all over the board. So yeah, it's quite interesting. So to theorise, but apparently it's well known as that fuse for blowing unexpectedly and for no reason. So there we go. Anyway, I've just got the information now from the service manual describing how this works, which comprises of a transistor Q1, which when I look here is this transistor, which is this surface mount SMD device, and then we have then this device, and that device is Q2, and that's Q3, this device, and Q4. Q2 is a 2SC 1971, and Q3 and 4 are 2SC 1972s. So I think I might clean them up, these transistors. There's a bit of light flux residue around the legs, but I'll clean them up anyway, just in case there's anything that shorts out on them or whatever. But anyway, the description is for the transmitter final amplifier for the VHF and HF section. It says that the final unit is comprised of an HF and VHF band final amplifier, an antenna tuning matching circuit and power supply circuit. The low pass filter section and antenna tuner detection circuit are located in the filter unit, which is in the rear of this board. It says the 1.8 to 144 MHz band is amplified by the final unit, but it operates in the broadband up to the drive amplifier. So if you remember it, earlier on we looked at the diagram, we've got the early stage transistor, then this, and then we have a broadband power amplifier section here, which is then switched by this relay, and then will drive ultimately the VHF section or the HF amplifier section. So that's where the switching's done. So basically everything right up to here is all bands, as in from 1.8 megahertz to 140 something megahertz for 2 meters, and this relay switches between either amplifier. Anyway, it says the 1.8 to 144 megahertz band is amplified by the final unit, but it operates in the broadband up to the drive amplifier, which is these. The final unit amplifies signals using independent amplifiers in the 8 to 50 megahertz and 144 megahertz band. The amplifiers are switched with a diode switch D1. So Q1 it now talks about, which is this surface mount device, which is just there. It says this amplifier uses a FET. It has a frequency characteristic so that the gain increases in the 144 megahertz band. That's all it says on that one. The Q2 here, which is our 2SC 1971, is a pre-drive amplifier. The amplifier uses a bipolar transistor. It has a unique frequency characteristics. So that's all it says about that. Q3 and Q4, which are these two, it says are referred to as drive amplifier. This is a push-pull type amplifier. It amplifies a signal with a broadband up to the 144 MHz band. Then the signal is branched to the HF and 144 MHz amplifiers through a relay, which is this. Q6 and Q7, HF final amplifier, which are these two transistors here. And you can just about see them under these big resistors. It says this amplifier uses a bipolar transistor with push-pull. It amplifies a signal up to the 54 MHz band using an output transformer, which is this, with a coaxial cable. And that's how that works. It's using the transform between the inner and outer of a coaxial cable driven through this ferrite core to act as an RF transformer at high power. It outputs a signal to the low-pass filter section through an effective and light matching circuit in the 50 MHz band. So that's when it obviously outputs then beyond this into this section here and this for the matching. Okay, so now we're talking about the 144 MHz amplifiers now, which are these two. It says Q101 and Q102 144 MHz final amplifier. A 144 MHz band signal passes through the high pass filter and attenuators, and the branch circuit with 2 amplifiers. So it basically comes in here, gets split, and then ends up at the final amplifier. It says it functions as a parallel amplifier that branches a signal with the same phase, amplifies it with the Q101 and Q102 amplifiers, and resynthesizes it. As a result, a 100 watt output is produced. Since the output matching section is a low pass filter type, it attenuates harmonics as well. After the output has been synthesized, it detects the power, the progressive wave and reflected wave with the directional coupler. Now, I think I did see the directional coupler somewhere down here. There's a bit of a track down there, and that, I believe, is where the yes, it is. It's just there. You might be able to just see it if we just adjust the camera a little bit. It's in this section here. It's just there. This strip line down there, and there's some components which you can see. So that's comprises the directional coupler. And it says that goes then. It says it detects the power of a progressive wave and reflected wave with directional coupler according to the strip line, and outputs it to low pass filter section. So the low pass filter section then, which is all this sort of relays and capacitors and inductor switching, plus what's at the back for the different bands. In the 1.8 to 50 MHz band, the signal passes through the low pass filter, and basically it shows us different tables in the service manual as to which low pass filter switched in. And then it says it is an independent low pass filter circuit and an antenna changeover circuit for the 144 MHz band. The signal output from the low pass filter passes through the detection circuits and transmission reception changeover relay K1, the antenna tuner changeover relay K3 and antenna changeover relay K4, and is output to ANT1 or ANT2, which is obviously the 2 different antennas. And it talks about the progressive wave and reflected wave output circuits, which is part of this directional thing with the antenna tuner detection circuit. Talks about the ALC, which is obviously part of this. It says the signal is detected by L7, D3 and D4. A voltage output corresponding to the progressive wave and reflected wave is produced by synthesizing the magnetically combined component by L7 with the corrected electrostatically combined component by TC1 and C9, and detecting the resulting signal. It is adjusted by TC1 so that reflective wave voltage under a 50 ohm load is minimized. VR1 adjusts the frequency characteristics of the 50 MHz band. These outputs are synthesized with detected output of a 144 MHz band and are fed to the TXRX1 unit. Antenna tuner detection circuit. The passing current is converted to voltage by L9, and the voltage is stepped down and detected by L10. One of these components is buffered by Q1 and Q2 and is rectified by Q3 and Q4. The input to the phase comparator IC2. The IC determines the IC2 Q output H or L, high or low, according to the phase difference with a D state flip-flop. The other component is detected by diodes D10 and D11, and the amplitude difference is compared with the comparator IC1. The capacitor capacitances on the input side is changed according to the phase difference detection output, and the capacitor capacitance on the output side is changed according to the amplitude difference detection output. So basically it's saying that it does a comparison with the reflected signal forward and reflected. It's looking at both, because we're using SSB AM modes as well as FM modes. You know, it's obviously got to be able to detect transmitter signals when it's broadcasting in AM or in SSB modes, where the RF power's varying massively with speech. So these capacitors, which you can see here, along with these inductors, these series inductors, and obviously some more capacitance here, which is this bank, they're all switched in by these different relays, and so thus it can change the what is the antenna impedance if it's mismatched, not to 50 ohms, it's using a long wire, or perhaps using ladder feeder as opposed to coaxial cable for HF. Then it can obviously match the output of a transceiver to a balun, or an unun, or a balun, you know, for high impedance. They will be presented by a long wire, for example, or a vertical radiating element, depending on whether you'll be using an external ATU. Obviously this does away with having the necessity for a external ATU to some extent anyway. So that's quite an interesting little thing. So but at least we've got a bit of an overview now of what goes on with this fuse, how the amplifiers work, and I think it's just a case of me now just replacing this fuse. It's a shame really they didn't leave the a bit more leg on that fuse down there, because as you can see it's soldered directly into the board on this end. Had they left a bit of lead like this, so this body was higher up, for example, I could have just snipped the bottom of the fuse and soldered the wire directly onto the new fuse and bridged it back onto the, you know, the top board, which means now I've got to take all this board out really in order to remove this properly and replace it with another fuse, and that means more work, a lot more time involved in being able to replace that properly. But before I do that, what I'm actually going to do, just to confirm it is this fuse that's blown. I mean, obviously I've got continuity between here and the amplifier circuits, you know, these transistors. What I need to do, just to verify there isn't a print blown underneath, I think it's on the diagram, which we'll look at in a minute, I think this relay here switches the supply on to this fuse. So what I'd really like to do is measure between, just to make sure the fuse isn't blown, is if I can find a point where the feed coming out the relay would connect to the fuse underneath the board here, is to put a continuity on from there to the top of this fuse to see whether or not we actually get continuity, because I've had things like this before where sometimes it looks like the fuse is blown but it isn't, it's a track underneath that's popped, and of course you go replacing the fuse, and if you're not careful you might find that you put it all back together and it still doesn't work. So I just want to, you know, double check, I want to, you know, cross the T's and dot the I's and just make sure that that fuse is definitely blown and there isn't a track connecting to this this relay here which switches the supply onto that circuit. I mean, I'm probably over egging the pudding, but I mean, as far as I can see, it's probably blown that, and I just need to replace it with another cartridge fuse. But just need to verify before we start ragging things to bits. Okay, so according to the circuit diagram, the best place where I can get onto the this bottom part of this fuse is basically, at the look of it, an inductor, because this relay here has got no exposed parts on the top part of the circuit but I can get to get to this line here that comes up and connects to this fuse on the, this bottom bit of the fuse is the bit that I can't get to because of the print on the circuit board. It's underneath and the fuse is just literally hard up against the circuit board here, so there's no real contact surface, although I do have a way of getting that by breaking through the paint on the fuse bottom to get an electrical connection, which I'm going to do. These voltage regulators here, amongst the others, are all under the board itself, so you can't get to them, but this line, if we follow it down, it does continue down here, and we get to an inductor if we just follow it down, which is this L205 there. So this inductor here I can find on the circuit board. It's an inductor that's mounted on the top side of the circuit board. So in effect I can go on either side of this inductor to measure continuity right the way up on this track via the relay that goes to this fuse here. So if I just zoom back in on the radio, so basically L205, because that's the fuse there, this green thing, L205 is this green beaded device there. So I can connect between one of the legs on that and the bottom part of this thing. And I've got the meter on continuity mode, and although the beep is not very loud. So this looks to me like as if it's the best option really, just to try and verify there's no trap broken. Okay, so I've got that verified. I just want to see what I'm doing. So just move my magnifier in place. So I'm just going to go on that L405 there, and then I'm going to try and break through the paint by pressing on. These are very fine pointed probes, so they should just be able to penetrate like needles at the end. I know they look blunt on camera, but I'm sure you they're not. They're very, very sharp. So I'm just going to put it on the bottom of that, just to see if I can break through the paint that's on it. There we are, look. So we have got continuity. So that's good. That means that, of course, the track underneath isn't broken. So to replace that now, I've got a choice. I can remove the board completely, which means I'm to disconnect these ribbons. Not a great fan of doing that, particularly on old equipment like this, because these will get quite brittle. You pull on them, they can break easily. They're the devil to push back in and get connected back again. But I'm going to look at that anyway, the options. Then I have to remove all the plugs and connectors and things that are on the board in order to get it off, and then remove all the screws that hold the transistors down. Some of the transistors on here I've got insulators on them, and some of them don't, because some of the tabs are not meant to be connected to ground, so therefore it's remembering where they are. There's also the fact that when you're retorquing the screws back up on the PA transistors, you can over torque them and end up damaging them. So I may decide just to on that fuse on this bit, just for ease, to prevent another catastrophic fault from occurring, I might just be tempted to underneath at the bottom there, I'll just be able to see if I can get in on this camera. I might be able to chop the fuse at the bottom, exposing the cup at the bottom, and then solder to that a new fuse in then across here. So basically cut this lead and cut the bottom bit, and then just solder on top of the board then to a new fuse in. And that'll save me having to take the whole thing out, because you can potentially cause further damage by removing this, by taking the board out. There's so many other things that can happen, particularly on older gear like this. And these ribbons, you can't get those anymore. They'll not be available from Kenwood. And I've had problems with these before when you try reseating them. They can break, and you get all sorts of weird faults. So I don't want to tempt Providence. I want to just keep it simple and go from there. Okay, so I've chopped the fuse out now. I'll show you what I've done, because before we take the board out, which I'm going to take the bull by the horns on this, I'm going to fit a new fuse and deal with these flexes, which we'll go through in the next part of the video, and all the other things. But I'm just going to show you the fuse that I've chopped out now. The reason why I've chopped it out is because my plan is to connect a current meter in series with the fuse connections. And so what we can do there is we can power the transceiver up and measure the current that's being consumed by this amplifier circuit here. And that way then, before we get to the stage of that process of removing the board and taking it all out, putting a new fuse in and putting it back in, if there's still a fault condition that may occur, that may be voltage dependent, for example, then it could blow the fuse again and all that work would have been for nothing. So rather than go down that route, what we'll do, we'll test the circuit first to see whether or not it's a fault condition that's still there. If it isn't, then we're good to take the board out and obviously replace the fuse. Now, looking at the fuse connections here, if I zoom right in, you'll see that I've chopped out what is the fuse holder, the little fuse, and there's a little bit of exposed connection at the bottom, which is like the bottom cup of the cartridge fuse, and then there's this actual lead. And if I get in at a different angle, that might explain it a bit better there, look. So we've got this lead, this wire, and I'm going to solder another wire coming off just here. So we've got two nice wires then that I can put my crock clips onto, and then we can do a current measurement. Now, I do have some fuses, but that's rated at 5 amp. I've got my fuse draw out here, and let's have a look here. These look all cartridge fuses anyway. I keep some fuses in the workshop, the rest of them are all in storage boxes in my storage container, so trying to get into there is a nightmare. But anyway, I've got plenty of cartridges, so that's not what I want anyway. I don't think I've got any, they're all rated differently. And then we've got even more fuses here. Now this is a type of fuse that I want actually, that type, because that's what should have been fitted. Because there's a circle, it does actually show in the circuit diagram it being a circular fuse as well, hence the reason why we've got this circle here. So it should be one of these anyway that's in, but what's this? What rating is that then? These 2 amps? Yeah, 2 amps I'm afraid, so they're no good. Let's have a look. Cartridge fuses, more cartridge fuses. Now then, these look all that. Let's have a look, see what these are. I think these only rated at a couple of amps as well. Not sure on those, but that's too big. And we've got these again. What are these rated at then? 1 amp. Still no good. Blade fuses, fuse holders. It's like cartridge fuses again. More blade fuses. Have a look here. More cartridge fuses. Yeah, these are boxes of cartridge fuses as well. Different current rating. Again, another 1 amp massive fuse. I don't seem to have what we need, so I might have to spend some pennies and see if I can find some 5 amp versions of those fuses. Who knows? I don't know, there might be some in the bottom of here somewhere. It's just finding them, isn't it? That's the thing. I should sort them out really, proper categories, but I just haven't got the time. So what's this at the bottom? These little packets. Nope, don't have any. So looks like I might have to order some if I can't find any. Back soon. Okay, we're ready to solder onto this bit of available solder contact just on the PCB there. Now, obviously, I don't want to melt this connector, so I have to be careful with the soldering iron and this wiring loom. So the best thing to do with that is to unplug it from the board, just gently tugging on it on the plastic shell, and then get the wiring loom to come off. And that way then we don't risk melting it, because it's easily done. Took that out of the way nicely. As I say, we've just got to be careful with this connector there that we don't melt it if we get the soldering iron too close. So the soldering iron's on. I've got a bit of an old diode that I've found in my parts bin, so we're going to use the lead off of this diode. I've already put a bit of solder on the end just to tin it. and then we're going to just solder that in place and then chop the diode off then, so we're just left with the lead. So that's what we're going to do now. And what I'll do as well, I'll just remove this blade fuse because that's quite prominent and could get in the way. So just making sure we don't cause any damage, because when you're looking at the soldering iron, the nib on the soldering iron can touch things, plastic things that are nearby, and you'll melt things, and it looks very unprofessional. So we need to stay professional at all times. And we've got some solder, and now we can go in and just solder onto here first, I think. So we just got to be really careful when we're holding the soldering iron that we don't touch things, so we just have to be extra special careful. Now this shouldn't, I'm hoping, shouldn't represent too much of a problem to solder onto, and I just hope that we can get on it. Yes, got a bit of solder on it now. Now, to prevent burning my fingers, I'm just going to use a pair of tweezers to hold the diode, because we don't want to get smoky fingers. So let's just have a look. Just watching where we're putting the soldering iron. Just bend this over again a bit further that way, and then let's see whether we can just get a bit of purchase on that and just solder it in place. Of course, this damn thing keeps moving. These tweezers are not too good, you know. Sometimes it's better to use long nose pliers than tweezers, because they get more of a purchase on the component. So let's just try and get on there now and just solder the damn thing, get it going. There. I think I'm making a mess of this with the look of it. Just need some more solder on it, I think. There. Right, so we soldered that. That's now in place, and so touch wood, should be able to snip that off and then get some crock leads on it, get a bit of purchase for a current meter. Okay, so we've got the crock leads connected into the top of the radio now for the ammeter, and that's going back to this ammeter there, which is on the 10 amp scale, and we've got then the output of the RF on HF linked all the way up to the Marconi, so we can take a power measurement. Now what I'm going to do is I'm going to power it on now, and we're just going to see what current has been taken when it's on transmit on HF. So I'm just going to set that measurement up now, so we'll key up the transmit on the radio, and then if I change the band, we'll go down to we'll try sort of 14 megahertz. It's various ones. You said 21 megahertz then, and then we'll change the power to reflect what RF power it should be doing. So let's have a look here. I think there's a power button there. We are, look. So it's at 5 watts at the moment, but we can adjust that right up to, you know, sort of 100 watts. So we'll leave it at 5, and I just want to see now what current it's going to draw at. So I'm going to press the torch switch after I've set up the mode. So we'll put it into FM mode, which it's currently in FM. Okay, so now I'll transmit on the microphone, and it's actually keying up, doing 50 milliwatts on 20 megahertz according to this. So there's something not right. There's no current being consumed. So am I measuring it right? Let's have a look here. I think I've got that's my meter not set up properly. So let's just have a look at this just to see what's going wrong. So that's current AC, that's current DC, And if I key up again, there's no current being drawn, which is interesting. I just disconnect that a second, so we haven't, in theory, got any supply going to the amplifier at all. When I key up, there's obviously no transmission now, so it is going via the meter. It's not like as if a fuse in the meter's blown and it can't measure current. So I don't know what I've done wrong. Let's have a look. Current DC auto, that's milliamps. Oh, I might have to select a different range, because I could be on the low current range, because it's in the milliamp range on the meter. And I just need to work out now how you switch between the range. There's a range here, look. It says auto. That's the amp scale, you see. Now I'm on the amp scale, I'm measuring 4.5 amps there, even while it's in receive mode, which is interesting. That's odd. 4.4 amps. What is it when I key up then? 4.9 amps. There's just nearly 5 amps on 5 watts. And then in receive mode, it's consuming 4.46 amperes. So that's strange, because I haven't got the mic keyed, you see. And when I press the torque switch, 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. It's only doing 50 milliwatts as well, so we're getting 4.8 amps being drawn on transmit, and only 4.4 amps being drawn. Right, so there's something not right. There's something not right. So I think we're going to have to look further into this, and I'm just going to switch the power off now, because I don't want any smoke to appear, and then we'll see what's going on. But there's obviously some quiescent current being drawn by what I'm not sure. So I'm going to consult the circuit diagram again, and I'm just going to have a feel about with my fingers in receive mode to see if I can feel a transistor or a particular component getting hot. So that's what we'll do next. Okay, so we're back to the diagram again, just to consult this. Now, looking at the configuration of the circuit, we've got this relay here, K201, and this is a constant supply rail on the top here. This rail, this is basically raw DC, which comes in from B+, which is the big thick red wire that we see soldered to the board or fastened to the board. So the supply comes in on the top. We've got it going through the relay and then coming to this point here. Now obviously it then enters these voltage regulators, which are various voltage regulators for different system components. So this relay is not there to switch the TX on and off. In other words, when you press to torque, this would close and thus connect the supply up to the PA circuits. That's not the case. This is actually a relay what's enabled when we power the radio on, although there is switching here, and I think this is so that it can be shut down, the radio, basically. It isolates all the supplies to the circuits, even when the DC power supply external to the radio is left in the on condition, so that it's not running internally, even though the microprocessor is shut down. So it disables this relay, which kills the power then to everything afterwards. So we've got this line going up here. Although it crosses this line, it isn't actually joined to it. That's why we've got the black dots. That symbology means that the track is joined to at these junctions. So it crosses this supply rail there, it goes across that, doesn't connect to it, goes through the fuse, which is what we're measuring now in this measurement, and then it goes to this rail here along. This is the hot rail that supplies power to the 4 transistors. And so what happens is that it branches to the left and goes through L4, which is this inductor, which then goes up to obviously this FET. This is a surface mount device. I can't see that drawing 4 amps on its own, otherwise it would be a burn charcoal. The other line goes via L6 via this transformer to the collector of this 2SC1971, and likewise branching right here we go through numerous capacitors, a couple of electrolytics and some non-electrolytics. We branch out this way, again some more capacitors in parallel, centre tap of this transformer where we feed both collectors on these 2SC1972s, which are Q3 and Q4. Now the rest of the circuit obviously is confined in this area. Again, you know, we've got biasing as well here, which we mustn't forget about. So on this line as well, although it's not connected there, it shows DC bias coming from the switching diode. So depending on which band selected, either way the bias is applied via this diode, and obviously in this case it biases this FET on, and that's unsettable in this context because that's got fixed potential dividers both top and bottom, and then we're feeding a voltage in. And likewise, as we advance along here, we've got another bias line going in there which comes up to the base of this 2SC1971, which is Q2. And if we carry on this line here, where it crosses over the red line, and we've got R26, it then enters the variable resistor VR1, which is a 220 ohm variable resistor, and this then via this diode then provides bias through the transformer windings this way to the Q4, which is a 2SC1972, and likewise the top way into that one. And so of course the same supply line provides a supply line, as we've just discovered, provides power to this section of the circuit. So with the fuse out, as it was earlier, the quiescent current draw of the entire transceiver is around about 3 amps, 3.2 amps I think it was when we looked at it earlier on the power supply. But while the fuse is in connection, then we're having 4.4 amps though thereabouts being consumed, even when the amplifier is not amplifying. So this must be something we'll have to look at with the biasing, and thus the bias into these transistors. If the bias is too high, then what it will do, it will produce more current consumption, because these transistors will be forced into conduction from the collector to the emitters, and thus they will then naturally in that formation provide a higher current consumption. Now it does seem a little bit strange, I must admit, how things are going on here, because these are in a push-pull configuration. So it looks to me, because we've got obviously to chassis ground there, so although they're in push-pull configuration, they actually are common emitters, so they go to 0 volt line or the ground connection. So obviously any bias that's fed on the base of these two transistors will force these into more conduction. So if the bias pot, which is this VR1 R220, is set too high and it's giving too many volts, too much current flow as well, then it will then enable these transistors to conduct significantly. And likewise as well, with this line here, this is obviously fed again from the bias circuit, but its fixed bias is that driver transistor, that 2SC1971, via these two resistors. This is just an RF feedback for RF gain control, so it basically has a loop gain. And likewise here we've got a capacitor resistor network, an RC network that allows RF to come back to the base, a small portion of RF should I add, not too much, it's just to give extra gain on these transistors to get as much juice out of them as we can. So yeah, it could be that there's a biasing problem, or it could be that the transistors themselves are faulty. and thus, you know, it would mean that they were drawing current when they shouldn't be. So I'm going to have to measure the bias in here. Now it does say, interestingly enough, which I find very interesting, it says R 0 volt, transmit 0.7 volts. So that to me would indicate that this line which comes in here, and likewise from the biasing circuit, oh, hang on, yeah, so the biasing must be switched. So though we have a constant feed to the collectors on these transistors, and that is constantly there, the bias itself via this R220 should be switched on and off depending on whether the radio is in receive mode. It should be 0 volts, so these transistors aren't receiving any bias. And likewise, when the transceiver's in transmit mode, naturally we want the transistors to be biased, so that then obviously we get the amplification. And thus we have 0.74 volts DC, which should be present on these transistors. So I'm going to have a look at that and measure that, because it could be that the fault itself is further back as we go back to this diode here, and it may be that there's something beyond this which is supplying voltage all the time here, which shouldn't be. And thus let's just have a look at where those lines go. There's two lines there, look, that are attached with those two black dots, and they go this way as well. Obviously there's various things here, some switching going on, another switch there, it comes down, goes along, so this is a line here, just keep going with it, comes up, and then that goes through a connector, and there's nothing seems to be connected that way with the look of it, so that goes absolutely nowhere with the look of things. And just make sure I've got the right line, you never know, I might have wandered off, it's quite easy. Goes up along there, look to that junction there. So this is a reverse current prevention switching circuit there, carries along and then obviously connects up to there. So yes, I've gone wrong, that connects up to there, so that's a different line. So let's start again, going across again there, this top line there, that goes up to here, to this VR102 bias control, which then obviously controls the biasing for these power transistors for the VHF, the look of it. Also it comes down, it looks like it comes from this circuit anyway, the look of it, perhaps, possibly, although it shows that being on the base, so that's probably an input rather than an output. It then comes back to here, we've got this line that comes all the way down here, it's all the way down, right the way down to there, and that is 14 TXB. Okay, so we know where that comes from, and then we've got this line here as well, which goes all the way down here, and this line again is HF TXB. So we've got the 144 megahertz, which is referred to as 14 TXB, and then obviously on HF, and we've got this where we've got HF TXB, and that then would bias on, obviously we've got basically 144 megahertz bias point here, and obviously the transmit supply for the HF side. So both of those go off along here and then enter this this diode. So no matter which band we're operating on, whether it's HF, which is on the left, or 144 megs on the right, then the voltage would pass through the diodes and then onto the bias line. So yes, interesting. So I need to check what bias we've got on this point, and probably the best way to measure that will be to remove this to prevent any uncertainties where things are leaking back through the junctions of the transistors to the base, because as again we've got this constant supply here from the relay down here when we turn the unit on. So this isn't to transmit supply, this is constantly there, and obviously it goes through these collectors. If there's some leakage between collector and base while ever this line's supplied, then that voltage would end up back on the base and end up getting back round and going. It wouldn't in this case get past that diode though, so that's fine. But insofar as this transistor is concerned, if it was leaking this way onto the base, it would get back onto this line. So potentially if there's any leakage between the collector and base, then it's likely to be that this transistor may be at fault. Possibly these, if there's some leaky bits going on in these junctions perhaps, but I think it may look unlikely because, you know, who knows, we can test that, but this diode would certainly prevent any voltage getting back to the bias point line, so that's obviously something we may look at later on. Might have to rule it out initially, but this transistor here is definitely a culprit if we've got bias collector volts fed back to the base and then obviously ultimately getting back onto this this line here, which would then find its way along here, get through this diode, and then obviously back into the bias conditions on both these transistors and bias these on as well. So food for thought. So I think what I'm going to do, my plan of action is to remove this fuse link again, which is what we've got a current meter across, so there's no supply getting here. Then I want to measure the bias on this line to see what voltage there is even in receive mode and transmit mode while ever this supply is not connected, and that will tell us if there's a problem with the bias. Then I'm going to connect the supply here and measure the bias with the transceiver in receive mode to see if there's any of this leakage that we just hypothesized. So that's what we'll do. Right, well, Kenwood have very kindly provided some test points, and if we just zoom in on the diagram a moment, you'll see that on the bias section we've got, if I can get the mouse pointer to work, we've got CN12 here, which is a test point that we can go on to on the board. Obviously this line will be taken via this diode to ground, so basically it'd be 0.7 volts maximum roughly that we could ever get on this line in theory, after of course this potentiometer. So what I'm looking to do is just have a look, see what voltage we've got there, then I'm going to find R26 and see what we've got on the other side as well. Now I might have to remove to isolate this QSC 1971 transistor, I might have to remove L6, this inductor, so that I can isolate that as well if we get weird voltages. So let's just have a look at where that is now on the radio. So that CN 12 is just here, and it's very difficult to see with this camera, but it's just there, look, this little lug there, that thing, CN12, just in front of that relay, wedged between the relay and this transistor. So that's where we need to go on now to measure our bias voltage. So we'll see what we get, and bear in mind that should not be present in receive mode, should not be there in receive, so whatever I'm not transmitting, we shouldn't be getting a voltage there. So that's what we're going to have a look at, and looks like the technical manager's arrived, so he may make an appearance, so we'll see what's what. Okay, so something really weird just happened. I've basically, what I've done, I went to have a bit of a break and I came back, turned the radio on in receive mode, and if you remember earlier it was drawing 4.5 amps continuously whether it was in receive or not. Well, I turned it on and lo and behold, the current went up to 4 point something amps like it was a moment ago, and then it just suddenly dropped, and there's now no current being drawn, which I find really strange. It just, I saw it come up, you know, when I turned it on, and then it just went down. It stayed at about 4 point something amps like it was a moment ago for about 2 seconds, and then just dropped off. Anyway, now when I go to transmit, I'll put it on the 2 meter ammeter band now, just to try it on there, just to see whether it was a band thing, but it wasn't. Now when I key up on here now, it's doing 700 milliwatts roughly on transmit according to the power meter on the Marconi test set on 145.5 megahertz. I've got it on at the moment, and we've got a current draw of 2.4 amps. And it is changing though, the current all the time, obviously, which it shouldn't be really to that extent. So something weird going on here. Can't quite understand what's happening, but we've definitely got a bit of an issue going on. So I'm going to measure some voltages now around those 3 transistors, Q2, Q3 and 4. But looking at the diagram anyway, from what I can ascertain, if I get the camera to stop moving around, it'd be nice. Let's have a look. I'm going to adjust this potentiometer anyway, just to see what happens. This where is it now? Lost track of where it is. Here we are, VR1. I'm going to tweak that just to see what we can get with the bias conditions. There might be something going on around here, this area. I've just been looking at this temperature compensation dial, because originally when I was looking at this circuit, as the bias supply comes in here via R26, goes through this variable potentiometer, which sets the bias current for this drive amplifier stage up here. But what it does as well, it goes to this CN12, which is a test point for measuring the bias volts, and then it goes down into this diode. Now this doesn't have the same symbology as an ordinary diode, but yet it's not a Zener either. So I think this has obviously been a temperature compensation. It must be some kind of special diode that doesn't work at the same characteristic as a standard silicon diode, where it would have in this configuration a 0.7 volt maximum potential across it, because obviously it's in that configuration any voltage here would be dragged down and clamped to 0.7 volts in that configuration. Or should I say orientation. Now, but it does actually clearly say that it is a temperature compensation diode, so this may not be clamped at 0.7 volts. This might be higher voltage. As a matter of fact, it is, because if we look up here, that can't be clamped to 0.7 volts, this line here, because if it was, it would never make it through this diode, because obviously, you know, a normal silicon diode has a voltage drop across it to 0.7 volts. So if this was 0.7 volts coming in, 0.7 volts minus 0.7 volts is 0 volts, so we don't get any voltage coming out. So this must be a higher voltage line than you know, would be clamped at 0.7 there. It must be a couple of volts or something there maximum. By this potentiometer. So that goes up through this diode, and ultimately after it's whizzed through this transformer on both directions and gone to the base of each transistor, according to the measurement diagram there, we should be getting 0.7 volts on transmit roughly on each base, and in receive 0 volts. So we're getting anything in receive mode. Now we were a moment ago getting 4 amps current consumption, as if some biasing had gone wrong here and it was somehow leaking these transistors. Maybe that's what the issue is, or there could be some contaminants between the pins that's causing some kind of leakage across the collector emitters, or the base collector junction more likely, and thus we're getting a bit of resistance across the collector base on both sides of the transistors, which potentially biasing them on, causing them to conduct current from collector to emitter, which is obviously the down to ground chassis. So these would consume current even in the receive status, because obviously there's no bias provided in receive, or there shouldn't be. So we'll just confirm that now. So if we just go back to the radio a moment, I'll switch the light back on so we can see what we're doing, and then I'll just have a look here, see what we can get with this radio. So now then, see if I can just come out a bit using this. So we've got a bias potentiometer down here next to the fuse, which is VR Is it 1 or 2? I can't remember now. It's VR. Where is it? VR1. There we are. So the bias potentiometer's there, which I'm on to now. This is where you need 3 hands, because I'm trying to measure, adjust and transmit at the same time. So let me just get the microphone in my hand and that onto there. Right, so let's go on to the CN12, which is the bias pot test point. That'll tell us what's going to the bias circuits. Well, it's in receive mode and we're not getting a voltage there, so at least that confirms that you know, there's no voltage that's there in receive mode, which there shouldn't be. Now in transmit, keying up now into the, press the top button on the transmitter, and now we're getting 1.5 volts on CN12 after that potentiometer. If I adjust the potentiometer fully counterclockwise, now we're hardly getting any current consumed on the ammeter. It's 0.5 amps. I'll just move the camera a little so we can see that. There we are, look. So on here, on there, that's the current meter. We're only getting 500 milliamps drawn fully counterclockwise on VR1, the potentiometer. Now if I start to turn it, the bias is 1.3 volts at the moment. It's now starting to increase the bias to 1.4 on the flute meter, but yet on the, yeah, now we've got definitely 1 amp draw there now, 1.5. We're getting quite a bit of current. That's maximum 2.6 amps. I can't get the 4 amps I was achieving earlier, so that's very strange, is that? Very strange. So that's 1.5 volts. Very strange indeed. So, very odd is that. Very odd, very odd, very odd. Right, okay. So, if I go now to Q4, or 3 on the base of the transistors. So, this is, I think, Q4. On the base, there's nothing there as per the diagram. It says receive 0 volts. If I key up the transmitter, we should get 0.74 volts, it says. Well, we're getting 0.79. So if I turn that bias pot so we get 0.74, let's just adjust it so that it matches that. Although I can't see it being an issue. 0.74 volts there. It's drawing 1.73 amps. Let's go on to the base on the other transistor. Oh, hang on a second. Let's go on to the collector on that transistor and just check the voltage there. There should be full supply voltage 13.6 in transmit. That's in transmit now. It's still 13 volts. Yeah, so that's working. And that corresponds with the voltages in the diagram. So that's correct. So the biasing conditions are okay now, although they weren't earlier, clearly. So there's something going on, whether we've got a transistor that's leaking or we've got some contaminant on the board, which does actually cause the transistors to consume current. I mean, don't forget, the fuse is only rated at 5 amps, and it was drawing 4.5 amps even before we started in transmit. So once everything's fully functional, even in that fault condition, the circuit would definitely consume more than 5 amps, and hence the fuse would blow. Now, I did find somebody, as I said earlier, that was selling these fuses, and they did say that there was a known problem with contaminants on the board causing short circuits through the cleaning process. So I wondered if there's something gone on in the legs, between the legs of the 3 legs of a transistor. If there's some contaminant got between them, and it's causing some conduction, some resistance between them. So they might need resoldering and a clean with some, refluxing, resoldering, and then a real good clean with some isopropyl alcohol. But, you know, if that were the case, then we'd be getting RF power, which we're not. We're only getting a few hundred milliwatts output on any band, really, other than UHF. So, although there's 2 different RF power amplifiers, themselves finals, the pre-driver itself and the driver doesn't seem to be giving enough RF oomph. The DC conditions on the drive amplifier, the 2 Q3, Q4 transistors that are down there, they seem to be okay DC wise, but are the RF conditions correct? If the DC conditions are correct, normally the RF would be, but I have seen transistors that do or other faults around the transistor which do give problems with the RF side. So the next one to check is Q2, which is a 2SC1971 that drives both of those transistors, and it's just sort of hidden a little bit sort of down there. You might be able to just see it, just hide in there. That's where it is. So that is Q2 on the diagram, which is this one on the left. So that's there. I'll just point to it on the schematic. That's just here, look, this transistor. So I'm just going to go on to the base there and measure the voltage that it says it should be. So the pre-drive amplifier should have the same roughly, nothing on receive on the base, and 1.66 on transmit. So let's just have a look at that then and see what we get. So if I take the probe again, I'm just going to have to use my magnifier because I can't see the camera's approximately 2 feet away from the radio nearly. So in order for me to see it from that level, it's quite an achievement even for me with my eyesight. So let me just see if I can get on that transistor a bit and just have a look and see where we are, because it's almost impossible really. Just bear with me. Right, we're back. So we're on the base now of the Q2, the 2SC1971. We'll transmit because there's nothing there on receive, and we're getting 1.72 volts. It says we should have approximately 1.66, so that's slightly higher than it says in the manual. Oh no, it's dropped down to 1.67 now, and it says 1.66, but initially it was higher. Let me just unkey, nothing then receive, transmit, and then we suddenly get the higher voltage of 1.7, but then it drops down to 1. Okay, well I think that's acceptable. Okay, I'll now go onto the collector just to make sure that it's got a collector supply, and then we'll see what we can see there. So that there is the collector now, and we're getting 13.6 volts in receive, which we would do because obviously that's getting the full supply, and on transmit we're getting 13.6 volts for 13.05 now, so that's okay. So yeah, that seems to be okay, the DC conditions. I think the next thing I could do really is to test the RF side, so we could use a diode probe, and we could, just by going onto this, if I can get this camera to move better, stop messing about. Right, so let's have a look at the diagram again. So I could get a diode probe. There's a couple of ways I could measure here. I could get a diode probe on the base of this transistor and then compare the measurement on the output. So we could rectify the RF into a DC level, and then we could check the gain of this transistor, and likewise we could do the same with these two, check them, see whether they're performing at RF. We obviously should get gain across them in that configuration. The other thing I can do is I can get a piece of open-ended coax, connect it to the spectrum analyzer, and what we'll do is we'll have a bit of tape over the end of the coax inner, so that it can't physically connect a signal to the coax, but we can put the coax next to the conductor on the leg of the transistor to sniff RF at a very low level to see whether we can see any RF gain between the base and collector. So we can sniff here and then sniff there, see whether we get an amplitude difference between the both sides. So there is that. And the other method is direct connection. So we could, where this resistor is here, connect an RF coax directly across the braid to this area in the centre of the coax here, and then feed that off then to an RF power meter, so we can measure RF directly. And then likewise on here we can do pretty much the same thing, probably at this junction here on the feedback circuit, the inner of the coax measured in there, or we could have a separate capacitor we could solder there off to an inner of the coax then to go off to an RF power meter. So there's potential to do that. And then likewise we can do the same here, so we can see what gain we get across these devices. So I think now we've established the biasing isn't the issue insofar as what's coming in externally. I do wonder though what's gone on, because obviously when we were making the measurement earlier in receive mode, this was consuming some current, and I don't think it would have been this transistor here that was consuming it, because I touched that transistor and it wasn't getting warm. These two were getting warm. I did put my fingers on them. They were only getting mildly warm though, because they're bolted to the heatsink like the other one is. But to sink 4 amps, 4 point something amps of current, then I would have thought these two would have to be doing it, because that other one would not be able to handle 4 amps of current on its own without getting really hot, and it wasn't. So I think personally it must be something to do with these two transistors here. I'm tempted to resolder them because we're not getting much RF power, because I could go on to here where this relay is here. The signal path comes out the transformer and in this way, so technically I could solder a coax onto here and check what drive levels we've got on both HF and VHF, and that'll check the performance of the overall circuit after the transformer. So that's something I could do as well. So there's a few options I can play around with. The diode probe is the easiest though to measure the gain, because it's less intrusive and also it doesn't require obviously it's a high impedance as well to the RF, so you know obviously these circuits are matched to the impedances of the devices that they're feeding, not necessarily 50 ohms, because obviously we've got to match it to those impedance characteristics. So yeah, there's a few things I can do here, so I think that's what we'll have a play with. I'll have a think and let's see what we can do. Okay, well we've removed all 3 transistors now, the driver and the pre-drivers, from the unit, which are the 2SC1972s. There's 2 of those and 1 2SC1971. So we've got them out now. We're ready to do a test. I've got this little transistor tester here, which is quite handy for doing little tests. So we'll choose the 2SC1971 transistor, which is the pre-driver. We'll just bob that in and give it a test, see what it does, and in a moment it'll do its testing. Just takes a few moments to sort itself out. So there we've got a known good working transistor with the look of it. Right, test this 2SC1972 transistor. This is one of the drivers, as if you remember earlier. These 2 transistors, 2SC1972s, work in a push-pull configuration with the RF transform in order to then produce a reasonable RF level then to well, that's come back as a working transistor, so we're okay there. Okay, let's try this last one then. This again is 2SC1972, again part of this push-pull arrangement, and let's see what this one comes back with. It's taking a long time to test this one for some reason. Ah, right, so it thinks it's just 2 diodes. Interesting, doesn't think it's a transistor. Let's just de-socket it again just to check the connection and just make sure they're okay, you never know. And then put it back in. Try again. Test. Normally for a good transistor to return a result by now, but as you can see it's not doing that. It's wobbling a bit, so let's have a look. Yeah, it still thinks it's 2 diodes, so it looks like this transistor's faulty. We'll verify it now on the flute meter, but that's just a quick little test, you see. So looks like that 2SC1972 is faulty, so we'll just put that to one side. Yeah, interesting. Right, we'll do some measurements now. That in the radio, the 2SC1971 is a slightly different pinout to the 2SC1972, and I know that because the tabs on the 2SC1972s are the emitters, because they're bolted to the chassis of the radio with no insulator, and so presumably the left or the right leg on this transistor is a collector, and then the middle pin which connects to the tab is the emitter, whereas the 2SC1971, which is the pre-driver, does have an insulator for the screw that goes through there to hold it to the heatsink, and on the back there's like a mica washer that stops obviously this connection here, the tab, from coming into contact with chassis, which is obviously 0 volt or neg VE. So the centre pin and the tab, I think on this are the collector. So that's the difference between the 2SC1971 and the 2SC1972. So what we'll do, we'll just hook the meter up in a moment and just check the junctions of these transistors manually on that. Okay, so we've got the meter on now. I'm just going to set it to diode there. Press enter on that. So we're on diode now. This is a 2SC1971 transistor. So this transistor, I believe it's an NPN. I'm sure it is actually, yeah. That goes down to there. And I think obviously that's collector, emitter, and then base. Now I think as far as the package is concerned, I think it's, if we draw the package, we've then got the centre mounting hole, 3 legs obviously. Now because this is sat on an insulator, this tab, and it's integrally joined to the middle pin, then I believe that leg in the centre to be the collector. One of the outer legs is going to be the base or the emitter, and we can find that out because if we just simply probe, make the base positive and the emitter negative, then we should get continuity there, but we shouldn't get it the other way around. Likewise, we should be able to, if we test between the collector and base, we should again be able to see a diode that way. Now if I remember rightly, because this is a special RF transistor, there was an integral diode across the junctions, if you remember. I think it was this way, according to the tester that we looked at earlier. It showed a diode as well being across the collector emitter. That obviously would not be present on most transistors, you know. So, but on RF you do get these strange concoctions. So I believe one of the leads on the outer edge is going to be the base. So what I'll do is I'll make, I think it's, I'm hypothesizing the left one is going to be the base and the far right one's going to be the emitter. And so we've got a forward voltage there of 0.649 volts, which is obviously proving the diode between the base and the emitter, making the base positive and the emitter negative. If I then reverse that the other way around, so we do it the other way, there's nothing there, so that proves that must be the base emitter junction. Now if I go between collector and emitter, we should be able to measure this diode here, this diode as well. Now normally on most transistors, obviously if you went between collector and emitter like that without the diode, there would be nothing there until such time as there's a bit of resistance between the collector and base, and thus then it will conduct. And you can do a wet finger test where you can basically bridge the collector and base with your finger, and then it will start to conduct to the emitter then, and you can measure a low resistance. But this is a weird RF transistor obviously because it's got an integral diode, so I should be able to read between the collectors. So if we just go on the tab and then the emitter, I can read there, look, 0.6 volts there, but I shouldn't be able to get it the other way around. So if I go to the emitter there, I can't get it there. So that just proves that that diode's functioning there. Likewise, if I go to the collector and base that way around, I shouldn't get anything, but if I go the other way, then I should, if it'll stop moving around when I'm trying to touch it with my probes. There you are, look. So we've tested both sides of the transistor. We've tested the diode, if you like, across the base collector junction, and then we've tested the diode between the base and emitter, and we've also tested this add-on integral diode between the collector and emitter. So that transistor's good. Okay, now as for the 2SC1971, this is the one that showed working on the tester. Now that one, I think, so that's a 1971. A 1972, I believe, the center tab, again NPN, and then we've got the base collector emitter, and we've got obviously same package style physically to look at, but this one's a little different because, as I said earlier, we had this wasn't on an insulator, this tab, whereas on the 2SC 1971 it was on an insulator, you see, that went round it. And obviously there's an insulating washer on the nut, because obviously the collector on the 2SC 1971 is going to this transformer, which is obviously then producing with plus VE the voltage then to the collector of that transistor. So you've got the base, collector and emitter on that one. However, on this one, I believe this is the emitter, and obviously it's integrally joined as well to the center leg. So I believe that to be the emitter, and one of these is going to be the collector and base. So let's just have a little look on the meter. I think this had an integral diode as well, if I remember rightly. So there'll be a diode again on this one going across the collector and emitter junction as well. That's an extra diode, by the way, a separate one that they've added. So I think if I make the emitter negative, which is the tab obviously, and then we go then to the left leg, let's have a look. We've got 0.6 of a volt that way. If I make the emitter positive and this left leg negative, which I think is the base, then that proves that that diode junction's working fine. If I make the emitter negative again and what I think to be the collector, which is on the right hand side, then we're not getting anything that way, but we probably will if I make it this way, which is making the emitter positive and the collector negative. We're getting something. So that proves that diode is actually working, this extra diode that's there, that's integral. And so the plot thickens, if I then go on to, I can't get everything in the image here, let's just have a look. So we prove the base emitter junction works, we prove the collector emitter works via this diode. I just need to prove now the base collector works by going on the edge, the tab, the number 1, and then the end one, which is the collector. Yeah, so it should conduct one way, 0.593 that way, and then the other way it shouldn't get anything. So that's correct. So that's proved that we prove the base emitter junction, we prove the base collector base junction, and we've also proved this integral diode. So that's that to a C1972 transistor. So let's get the offending article, which is this one. This is a 2SC 1972 again. This is that last one that we tested where it wasn't playing ball. Now if I go just between, do the same tests again, because we believe the left pin, I should have drawn it here, would be the base, and that would be the collector. If I now go to the base emitter junction, so if I make the emitter negative, obviously, with the meter, and then go on to the base, we're getting 0.6 of a volt that way. If I make the emitter positive and the base negative, we're not getting anything there. Okay, that's good. If I go between the base and collector, one way, base and collector, we're getting a voltage that way, 0.6. So between the base and collector, and then if I go the other way, I shouldn't get anything, and I'm not. So the base collector junction's working fine, and it looks like the base emitter junction is working fine, because obviously we made the left leg positive and the tab, which is a center leg, negative. So that's that base emitter junction there. And just to repeat that again, look, and then making the base negative and the emitter positive, we don't get the diode. So let's check the diode now that's integrally added across the collector emitter junction. So again, this would mean, let's just for argument's sake make the emitter positive and the collector negative. Oh, well, here we are, look, we've got a short. So it's, well, not passing any voltage that way. Let's change it the other way around then. So now we'll make the collector positive and the emitter negative. And again, same thing again, look. This is a faulty transistor. So, yeah, see if I can just capture that in the image a bit better. But so again, collector emitter junction are these two let's see if I can get a better picture of that. So the collector emitter, base emitter collector, BEC. So no matter which way you go around between the base, the collector and emitter junction, it's basically that diode. This diode there is short, basically, with the look of it. Let's just go on to ohms on this meter, just to verify something. Ohms, enter. Okay, we'll just touch the probes together to verify that there's a short circuit. I don't know why it's reading meg ohms there. I think it needs to be on auto. There we go. Right, so if I short the leads out now, it should read 0.1 of an ohm. There you are, look. I don't know why it's on the meg ohm scale. These flute meters are a bit scatty. Should be reading ohms, not 0.1001 meg ohm. It must be something to do with the ranging. Let's have a look, see if I can. There we are, look. There, at last. Right. So if I go on to the collector, the emitter, sorry, make the emitter positive and the collector negative, then looks like we've got an 11.4 ohm short or resistance. If I go between the collector and emitter, the other way around, so I make the emitter negative and the collector positive, then we're getting the same again. So that proves that that transistor is faulty, that it looks like this integral diode has gone sort of leaky, got a fault with the junction. So that would explain the 4 amps being drawn, because obviously again we will have a collector going to the RF transformer, and then naturally that goes again to plus VE. So this is conducting between those two junctions there of effectively a very low resistance, and thus because the emitter is connected to neg VE, basically means there's going to be current consumed regardless of what's on the base. So I'm going to look now in my parts drawer to see if I can get these 2 transistors replaced, and hopefully, because better to replace them in a pair, because they normally, you know, do better that way. One will be tired anyway, even though it works, and the other one will be as knackered, obviously. So no point in just putting one transistor in a new one and then having the other one not quite performing well, and that might be on the way out anyway, because it's probably from the same batch, might start to fail anyway soon. So better to change those in a batch, if you like, from the same batch as a matched pair. This 2SC1971 does work. Now I do have some of those in stock as well. I may decide just to change that too, because it could be you know, just may circumvent issues later on. Although, you know, there's nothing wrong with that transistor. I might just bob it back in because it's on its own. But sometimes I think it's easier to replace things because, you know, if you've got the components, change them. But, yeah, so that's interesting, that. Right, onwards and upwards. Okay, so I'd look in the parts bin, and I didn't have any 2SC1972s in stock. The bin had nothing in it, so I've got a 2SC1971s, but not 1972, so I've had to buy some off eBay, and they've arrived today. So we're going to be taking a look at them, just to make sure they're genuine. It did advertise on the listing that they were genuine transistors, and the company that was selling them, I got good feedback for selling genuine transistors, and I know there's a lot of counterfeit RF transistors and things out there as well, but I've been quite lucky so far, so hopefully that luck will continue. So anyway, let's bob it in this tester and just see whether it works, and see if it's got the same internal configuration as the originals with that extra diode as well. Just testing it. Yep, looks okay. Not to be any issues there. I'll test the other one. Just get this one out, put that in. See what this one returns. Test that. Oh. Again, same thing. Start looking good. So yeah, I think we're on a winner. We'll put them in, see what happens. So we're back soon. Okay, so we've now fitted the new transistors, soldered them in. So these are the two 1972 push-pull driver transistors that work together via this transformer here, and we've got those two together, and under this heatsink blob here is this under this heat compound stuff, this white stuff, is that temperature compensation diode. This here is the 2SC1971, the original one that we put back in, and obviously everything else is there. These two cables here carry your HF and your VHF injection before then being amplified up by a transistor which lives down there towards the front. If I can see him somewhere down here, I think it's just there. Look, this transistor there is the transistor that deals with the amplification initially, and then that gets passed to this transistor via this transformer, then to these two transistors, the output of that then to this transformer. And one of the things to be aware of is the little relay there is the device which switches the signal between the HF power amplifier, which is these two transistors, or the VHF power amplifier final, which is those two transistors there. So that effectively switches between both sides, does that little relay. These two potentiometers set up the bias of the power amplifier, so we'll need to do that adjustment again anyway, just to make sure that's sorted out. I've fitted the fuse back as well. This time we've made it so it's stood off the board, so if that ever goes again in future, we can just snip the leads and solder it while it's on top of the board without having to take the whole board out to resolder it, put another one in. So I think we're ready to do some RF tests now to see whether it functions. Now I'm not expecting great results on the very low frequencies until I put the case back on the ATU. This is the ATU automatic tuner for the aerial antenna, and of course without the screws being in place in these earthing points here, then we're not going to get a good RF earth. So I'm going to put the screening cam back on, and then we can be confident of doing some proper RF tests then. Back soon. Now that we've fitted those transistors and we're now ready to do our RF measurements of RF power, before we obviously do that, I've put the cam back on, the antenna tuning unit, because it uses a lot of RF grounds, which are either lugs that screw the can down to the chassis as well as on the PCB. So that'll reduce any you know, inductances and problems where we get self-oscillation and other issues as well. So it's always recommended putting that can back before you do any RF measurements anyway. But I just wanted to briefly talk about these transistors down here. Now when we were looking earlier at these RF power transistors, if I just move that out of the way a second, we had obviously the driver, and then these two transistors here are the sorry, that's the pre-driver, and these two are the drivers, which then drive the final amps, which we can just see there. Now we've got the VHF power amplifier as well as the HF power amplifier, which are just beneath these resistors. And ultimately the driver section here, as we were looking at earlier, is a 3-stage amplifier, because we have which you can just see very carefully. If I just move the radio round a little bit and everything falls over as usual, but you can just see down here there's a transistor just there where my fingernail is. These are your coaxial inputs that are HF and VHF feeds in, and then it goes to this transistor here, which is switched on its input with a diode, which is down here on the board, which switches between these two feeds. This transistor amplifies all frequencies between HF to basically 145 megahertz, which is a 2-meter ham band. So that's a wideband RF amplifier. Its output is fed into this transformer here, and then we've got two transformers. We've got one transformer which feeds the signal input then into the driver, the 2SC1971, which is this device, and its output then is then fed to this transformer, which then feeds into both these devices here, 2SC1972s. They in turn have a transformer on the output to match both devices in a push-pull configuration, and then the output of that transformer then is fed into another transformer. But prior to that, it goes via this relay here. So this little relay, obviously, that looked at in the last section of the video, obviously switches the RF path between the VHF power amplifier at the top and the HF power amplifier at the bottom. So in the HF mode, the signal gets amplified obviously by all these devices here, pass through this relay after it's been amplified by these two transistors in push-pull configuration, switched into the input of this transformer here, which then obviously goes to feed these two RF amplifiers. Now obviously we don't need that kind of ferrite transformer on the VHF side, so when the relay flicks the other way to feed a VHF signal, that then gets fed into the input here by these two capacitors which set the matching for this stage. So what I would recommend, based on the fact that we have a alignment now to commence, is as long as everything's back together, you don't leave anything, you know, unscrewed on the motherboard. Any screws that are holding any devices down need to be in place. The screening can for the antenna tuning unit also needs to be in place. Then that will be the stage when you're ready then to do the transmit power measurement. Now obviously this radio is a very high powered radio. It can do up to 100 watts on CW, FM, upper sideband, lower sideband, and AM amplitude modulation. So, you know, the sort of current this radio is going to take is probably about 20 amps DC. So we've got a high current power supply on now. and that's the reason why we need that sort of high current supply, which is this supply here supplies about 40 amps maximum. So we've got enough current, if you like, in order to be able to get this radio to deliver its output. Now, to do the power measurement on FM and CW modes as well as sidebands, we're going to be using the Marconi 2968 radio communications test set. That test set has USB, LSB modes as well as AM and FM, so it's able to measure the power. It has a peak of 150 watts handling power, as well does the Marconi radio test set, so it does away with having to use, in our case, sort of meters like this. Now, obviously meters like this, one of the issues that we have with measuring sideband signals, USB, LSB, etc., is that we don't get the peak on this meter. This is made by sort of Bird, Coaxial Dynamics, which is all part of the same company, I believe, or very similar. This particular meter uses a sensor internally. Looks like we're going to get joined by the technical manager in a moment for some technical advice. But basically, the meter itself can read average power in that configuration. Now, Bird did produce a meter which is similar to this. I have one here actually, a Bird 43, and that Bird 43 meter that I have has got a special modification on it to read peak power on SSB, and we'll go into why that is necessary for measuring SSB a bit later in the video. But for the moment, what we need to do is we'll just leave this to one side at the moment. We'll use the Tetra radio test set that we've got up here, the radio comms tester, to do the measurements. Now, the first measurement that we need to do before we do anything else is the biasing for the RF amplifier. So I've got a section here in the service manual which shows us how to do that. So as we looked at earlier on the motherboard, there are sort of a number of potentiometers on the board which deal with all kinds of different things, and basically the technical manager has just directed me to which ones they are, and that is this potentiometer here and these two potentiometers there. You might just be able to see the one next to this blade fuse. They set the biasing conditions for the driver and the HF amplifier and the VHF amplifier, and so there's a measurement in the manual which shows us how to do that using the ammeter. So before we get on to the really hefty RF transmissions measuring hundreds of watts of RF power, we need to first of all keep the power on the transmitter to minimum by adjusting it to 5 watts, and then we need to put it into particular frequencies and modes as directed by the manual to then adjust these potentiometers. So we'll do that now, and when we have a look at the manual, it does say, if I can get this camera to move in the right place, it does say here final idling current for HF and VHF. So this is where we set up the bias conditions. So we need the radio to display 14.1 megahertz in the mode of USB upper sideband. We then need to set VR1 and VR2 to the minimum position, and then we need to go into transmit, and then we need to measure DC current, and this is the conditions that we need to look at. So VR1 and VR2 is the well, basically the VR1 is the pre-driver and the driver, and VR2 is the HF power amplifier, and VR102 is the VHF power amplifier. So what it's basically saying there is, above and beyond what the quiescent current is that the radio is currently consuming when it's turned on in receive mode, we need to then measure these currents above and beyond that. So this is in addition to the quiescent current that's being drawn by the transceiver in its operating condition. And so the specification as well is plus or minus 20 milliamps, so it's quite precise. We've got to make sure that we're within that tolerance, otherwise the biasing will be out. So first of all, it talks about setting VR1 and VR2 to a minimum position first, so that's what we'll do now. So if we go back to the transceiver a moment, and we'll just put the light on again so we can see what we're doing. And if we go to VR1, VR2 and VR102, which is these, we'll set VR102 to minimum, that VR1, VR2 to minimum position. Okay, so now we're ready to do a current measurement. And by turning the radio on, and then obviously getting to the stage where we can do a measurement now on the current meter. Now I've set up a power meter there, current meter, for measuring the current. So we'll get the technical manager out the way, and then we can turn everything on, and then we can start doing some measurements back soon. Okay, so the technical manager's now left us to give somebody else some technical advice somewhere else. So we can now turn the radio on, and we've got the ammeter on the 10 amp scale, which is in the top right hand corner there. So currently we're drawing 2.438 amps. So the test conditions in the manual say that we've got to set the frequency to 14.1 megahertz. So I think we can do that by pressing this, 14.1 megahertz. Mode needs to be upper sideband, so we need to press USB, upper sideband mode, and we'll set the power to 5 watts so that it's not doing anything that it shouldn't be, and that way then, you know, we'll just turn it down, which is this level here in the corner, so that's okay. So power's set at minimum, so we're not going to be, you know, that's another reason why the RF power needs to be set at minimum as well, because often most multimeters or DVMs have a 10 amp maximum anyway on the highest current reading that they can do without an accessory of a recurrent clamp. And so therefore, if you left a radio at a very high power and you were setting the biasing conditions while you're in transmit, if the radio was to just take off and start doing 100 watts and it's drawing 25 amps, it's going to exceed the current rating of your meter and probably pop the fuse at minimum, so, or damage it. So that's another reason why you need the RF power turning down to 5 watts when you're doing your current measurements, because obviously you don't want that issue of it just taking off and doing, you know, 100 watts and drawing 25 amps through your meter and then causing you other problems. So keep the power at minimum. Right, so we're ready now to do a current measurement, and it does say in the manual set VR1, VR2 to minimum, adjust VR1 for 700 milliamps and VR2 for 500 milliamps. Now there's a section in the manual that shows what the adjustment points are on the main board and what the potentiometers are and where the positioning is. So that I'm just looking at that now, and it shows that's basically VR2 there, potentiometer, which is closest to the HF power amplifier finals, and this down by this blade fuse, which is just hidden by this electrolytic capacitor, is VR1, and VR102 is this pot there, which is for setting the VHF power amplifier for the 2 meter 144 145 megahertz band. So okay, we've got the HF antenna output at the back connected into the Marconi radio tester, so we've got 50 ohm load presented obviously for the transmitter output, because we don't want the transmitter, if it does start making any RF power, going into an open circuit and thus creating high VSWR conditions. That's not desirable. Terminate it into 50 ohms. Right, just going back to page 112 in the manual, which is the page that tells us where we make our measurements. Right, so we're drawing 332 amps. We need to where is it now, 1112, here we are. we need to adjust VR1 to 700 milliamps in excess of what we've currently got. So VR1, let me just have a look, see what we've got with my magnifier. Right, so VR1 needs adjusting to 700 milliamps in excess of what we've currently got now, and VR1 is closest to me, which is a 1 here behind the blade fuse. So we'll just get the trimming tool on that. It's set at minimum position obviously, and what we need to do now is key the transmitter, and we need then to adjust its current to 700 milliamps in excess of where we're at now. So if I just go back to here in the service manual, if I can get rid of this, if another page has just popped up. Here we are. Right, so here we go. Right, okay, so we need to be looking at 3.032 amps or 3.03 amps. So we'll get the transmitter now, we'll key up, and now we need to adjust this potentially for our 3.032 amps. So that would then, we're nearly there, or a bit higher now. So 3 point, we'll call it just nearly there. Just got to get it 0. Right, let's have a look. It's just creeping up a bit. You've only got to breathe on this connector, on this potentiometer rather, and it right, I'm happy with that. That'll do me. Obviously if you were to speak into the microphone, then in SSB mode the transmitter's trying to broadcast, so if the audio is muted then that will be better. So there, that's that done. So now we need to move on to VR2, which is the bias for the HF amplifier, and then it basically says that we need 500 milliamps on top of that current. So we need to adjust, we need to add basically 500 milliamps onto that, which is then going to give us 3.532 amps. So if we go to this transmitter here, right, I'm going to key the transmitter up, pots at minimum position, so we now need to adjust that to 3.532. So we're just giving it a gradual turn. It might just suddenly take off. It's got a fair, oh here we are, look. The test set's starting to receive power now, so I've just heard it come up. So 3.532ish roughly. Oh, it's jumping past it. 5857, 53. Oh, we nearly had it then. There we are. I'm happy with that. Again, quietness, because the moment you start talking, the current will jump up and down as the mic picks your voice up. Right, just let it settle a bit, and now we'll just get it up a little bit more. Aiming for 3.532. Nearly there. There. Yes, damn it. There. Right. So then it talks about now the VHF high band, 145 megahertz. So it talks about going to 145.9 megahertz now, I believe. Right. 145.9. It then talks about, again being in USB mode, upper sideband. The power's jumped to 100 watts, so we're going to have to turn that down to 5, obviously. Okay, so then it says adjust VR102 for 1000 milliamps, or 1 amp quiescent current draw. So because we're now not using the HF amplifier as we were before, and we've moved over now to the what would be the VHF high band amplifier, we don't need to take account now of the current that was being drawn by the HF amplifier when we went in to transmit. Now if I key up, it's drawing 2.7 amps, so we need to adjust that now for 3.7 amps. Hang on a second here. Have I got that right? Oh, it's right. So it's consuming 2.102 amps currently. We need to adjust the VHF amplifier now to draw 3.1 amps on transmit. That's it. So if I key up the transmitter, which I've done, and just adjust this now for 3.1 amps. Okay. .1 amps with no mod. Okay, 2.1, key up, 3.1. There. So that takes care of that measurement. So I think now it's time to actually do some RF power measurements and then go from there. Okay, so we've set the power now to 5 watts, 145.9 megahertz. We put the mode to CW mode. We could do it on FM as well, which we will do in a more. We've connected the VHF antenna for the VHF high band power amplifier output to the antenna output to the radio test set. So ready to do some power measurements. And so if I just set the camera up there now onto that, and hopefully if this damn thing had worked properly, and we can look at the transmitter power. Right, okay, so we're an FM mod type on the power meter. So let's just have a look there. Right, okay. So basically in the top right hand corner where it says power there, that's what we're looking at. We're currently set to 5 watts on the radio. So what are we getting? Oh, near as damn it, 4.731 watts. Now there is a menu in the radio where you can make fine adjustments later on, which I'll show you, but that can then tune up, if you like, the RF amplifiers following this measurement to a more refined mode. So we're just going to check the power now. If I tweak the RF power up to that's 50 watts setting, so it's 46.8 watts, and that then is the 100 watts setting there, so it's doing 98.17 watts on transmit there, so that's pretty good. Okay, so FM, in FM mode, so let's see, 1 2 3 4 5 5 4 3 2 1 1 2 1 2 3 4 5, radio test, 1 2 3 4 5 5 4 3 2 1. So modulations there, deviation 4.5 kHz, roughly deviation 4.7. So that's there. So the VHF power amplifier is working. Right, so what we'll do now is we'll move over now to the HF and check that as well. I might check SSB actually on the 2 meter, see if we're already on that. So I might do that anyway. We'll move to upper sideband, lower sideband, etc. just to test the RF power on there. So let me just set that measurement up now on the radio test set. Okay, so we're ready to do a measurement now on sideband, upper sideband on transmit. So we're currently set up to do that. We'll put it on the 100 watt power setting. Now ideally you're meant to modulate the transmitter with a 2-tone, but I'm going to hollow into the microphone just to give an indication of the peak power. Now obviously on the sidebands the RF power isn't there unless we modulate the signal. And indeed, even when you do that by screaming into the microphone, depending on what syllable you're speaking and what the frequency component of your voice is made, it will depend on the RF power output that the test set can measure. This is the issue that we've got when you're measuring sideband transmitter signals on using just standard voice modulation on RF power meters like the analog meters. That they will not read the peak power unless they've got the peak power options on them or modified to do that. So this is why we're using the Marconi test set, because that's got the capability of measuring the peak power. But as I say, ideally the transmitter should be modulated with a 2-tone, 2 audio frequencies at the same time being transmitted into the mic input on the transceiver as an audio AF level, and then you would key the transmitter and that would then modulate the SSB circuits to maximum, and then obviously we'll get a more complete picture of the RF power. In this stage we're modulating it with a human voice, so naturally the variances in the voice will also directly reflect the RF output power as well, but I'll try my best. So we've got it set to 100 watts on 2 meters, upper sideband, and you'll see depending on what number I hollow into the microphone will depend on what the output power will be. So let's have a look here. 1, 2, 3. So you can see there the transmitter power is varying depending on what I say on the microphone. So that's the reason why obviously the RF power suddenly goes up to about 70-80 watts on one of the transmissions, and it was only I think 17 on another when I spoke I think with the number 1. So depending on the human voice and the frequency range, the harmonic content of the voice and the actual speech itself will also depend on the RF power output. So 4. So you can see they're doing the number 4. It averaged about 55 watts, whereas when I think it was 2, we were doing 77, 80, 90 watts. So 5, 3, 2, 2. So we're getting all sorts of different powers. So really, that's sort of a rule of thumb. It's just basically proving that the modulation is modulating the transmitter as it should be. Now, to do an absolute accurate measurement, we would need to probably make up a microphone socket, plug rather, that's got an audio lead on it that will go into the AF in output on the test set, and then we would generate a signal then on the AF gen output. and out of this port here into the microphone socket on the front of the radio with a tone, and then we will key the transmitter to see that modulation coming out. So that's basically how you would do that. So let's move over to HF now and see what kind of performance we're getting on HF. Okay, so we're ready now to do a measurement of the transmitter on 52 megahertz. We've got it in CW mode at the moment, set at 5 watts, and as we can see we've got a nice 5 watt almost carrier there, so with the RF power in the top right hand corner, and I think the bar charts might give a better example of that onto there with the RF power in this area here. So we'll adjust it now to 10 watts power. So as we can see we're almost at 10 watts, 9.66 watts. That's meant to be 15 watts of power, just a little bit underneath. That's 20 watts of power, near as damn it, but just a little low, which we can adjust later if need be in the menu. That's 25 watts. That's 30 watts meant to be, 27.2 watts. 30 watts, 35, that's meant to be, it's just a little over 30. That's 40 watts, so it's 35, lagging behind there a little bit, but not too far away. That's 45 watts allegedly, it's doing 40.17, so that's 50 watts, doing 45. That's 55 watts, doing 50 watts just about. That's 60 watts, and the radio's actually doing 53 watts there. And then all the way up, I'll wind it right way up now to 100 watts, and it's doing 85 watts. So does need a little bit of adjustment, I think, on that frequency band. So we'll have to look at that a bit later in the menu. I've just adjusted the ATU just to see whether we can get a bit better tuning. So let's see what we're getting now. 85 watts still, so it's not related to the antenna tuner. Right, so let's go down to 51 megahertz for the ATU. Right, so this is 51.770 megahertz. Again, if I just turn the volume down because we're on FM. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. So this is 100 watts transmitter test at 51.770 megahertz, and you can see it's doing 87 watts. I'll put it into CW mode, then we don't get the speech. Right, so that's 85 watts again. Next band is 50 megahertz dead. I'll just adjust the ATU. There we go. Right, so this is 50 megahertz. Put it onto CW. For some reason it keeps reverting to FM. So 95 watts there roughly on the 100 watt setting on 50 megahertz. So we'll go down now to 29 megahertz and see what that is on the 100 watt setting again. Or is it? No, it's dropped down to 5 watts. Let's have a look. What can it do? So that's 100 watts. It's doing 90 watts on transmit there on that frequency. Next one, 28 megahertz. Key up again into transmit mode, and now we've got 89 watts at 28 megahertz. At 24 megahertz, again the CW mode. 24, call it 25 megahertz, or 24 point, just set this up, 9 megahertz. And we'll see whether we can get it to transmit 100 watts. So that's doing 90 watts again. I'll just press the ATU, see if we get any better power there. 90 watts then, call it, on 24.9 megahertz. Next one is 21 megahertz, 21.010 on CW mode. So we're doing 83 watts, 82 point something or other. I'll see if the ATU can adjust it. Let's have a look. Now that's a maximum we're going to get out of that, 82 watts on 21 megahertz. Next one is 18 megahertz, and again key up the transmitter, and we're getting 88 watts at 18 megahertz. Next band is 14.1 megahertz. Let's see what power we get on this frequency. So we're getting 87 watts on transmit on 14.1 megahertz. On 10 megahertz, I'll just press the ATU. Actually, I'll just go back to 14.1 megahertz again and press the ATU. Let me see whether I could get any better than that. No, 87 watts is the most we're going to get on 14.1 with the look of it. Right, go back to 10 megahertz, press the ATU button, see if we get a good match. Just transmitting again, 87 watts again, seems to be sticking to that on 10 megahertz. 7 megahertz now, ATU. Put it into CW mode, okay, on to transmit. 86 watts again, 85.7 watts, 7 megahertz. Down to 3.5 megahertz. Press the ATU, into CW mode, transmit. Now I think it will be too low down for the test set to pick it up accurately, so I need to put in 3.5 megahertz. Let's have a look here. So we've got, call it 70 watts as the crow flies. So that's okay, 70 watts. Next one, 1.8 megahertz, CW mode, transmit. I'll put the ATU on just to see whether that gets it going. Yeah, right. Oh, hang on a second. TX frequency, 1.8 megahertz. There we go. So this is on the 100 watt setting. It's doing about 63 watts, but that's right on the limit, the lower limit of its frequency range. So I'm happy with that really. I can do some minor adjustments anyway in the menus. So that's that. Again, 14.1 upper side band. If we just go on here to I think it's RF test, SSB mode, then we'll select upper side band, and this time I'll just put a TX frequency 14.1 megahertz in, and we've got it in the 100 watt setting on USB. 5. Oh, RF test, SSB TX. There we go. 2, 3, 4, 5. 2, 3, 4, 5, 5. So we've got some good modulation there. Okay, so we will now move on to doing some more measurements. Right, we've set the radio up now with this Coaxial Dynamics RF power meter. You'll have seen in my other videos I have the Bird 43 meters, I have a Bird 5000EX, which is the modern digital version that measures, for example, digital transmission modes where we're using pulse modulation, or QAM, Tetra, DMR, Fusion, those kind of digital modes, P25, where we're measuring burst power. And so the Bird 5000EX digital power meter that I have is really good at measuring sidebands peak power as well, SSB transmissions, because obviously it's capturing the peak of the modulation envelope. So those meters are quite good. These are also really good for measuring RF power as well on the sidebands, but you do really need to be using the two-tone test with the transceiver, whereas I remarked earlier you'll be generating a AF signal into the mic input socket on the radio. I do have somewhere in a box a load of these plugs, but I can't find it at the moment, and I would normally have made up a plug with an audio lead going up to the radio test set to produce an AF input into there, and then we would key the transmitter, and that would obviously produce maximum RF power on the watt meter. Now I like using analog meters and things, you know, it's a bit old school, but I do like using them, and I even use this old current meter still to this day, even though on the videos I tend to show, you know, obviously the digital meters for more accuracy, but I do still like to use old analog meters like this, and if that's what you have, there's nothing wrong with using that. You know, if it measures accurate, that's all that matters. One note though on analog meters, I wonder if somebody can tell me what the issue is with both these meters, both the one here in front and the one behind is. Now if I just zoom in on the one behind a little bit, you might be able to have a look at the face on that meter and tell me what you think might be wrong with it, and take a good look at that scale and tell me what you think might be wrong. And likewise this one here, have a good look at that and tell me what you think might be wrong there. So obviously looking at the meter, before we do any measurements we need to make sure that the meter zero line is set up, and it's the same with the RF power meter at the back. It's actually reading a little bit off, and that's the reason why we have these mirrors behind the needle, so that we can do what's called a zero set with a little adjuster, and we can make the adjustment before we do any measurements, obviously, because if that's not adjusted properly then naturally we won't be able to get the meter to read correctly. And so that's the very first thing that should be done with any analog meter before you do any measurements, is to double check that, you know, that meter that you're going to be using is reading correctly. So in terms of the RF power meter, just move that out of the way. The setup here is we've got a 250 watt RF load mounted on that heatsink. We've got a transmitter being fed in on the left. We've got a 2 to 30 megahertz 500 watt rated pod in there, and then on the meter we're on the 500 watt scale, which is a second scale down from the top. So if I just move this a little bit, see if I can get a better image, although that might be interesting at this moment in time, just to see whether we can get the image the best we can. That might be better there, mightn't it? Okay, so let's zoom in there. So the first thing we need to do there is just adjust this needle here onto that first mark. Now it might not be, I can see it with the naked eye, but it's a little bit off. So we'll go into the adjuster, which is this little hole here, and we'll just adjust that now until it reads 0. That'll do. Near enough is good enough. Right, so now we're ready to make an RF power measurement. Now we're using this scale here, so 10 represents 100 watts, so this mark here is 100 watts, that's 100 watts, 200 watts, 300 watts, 400 watts, 500 watts. This pod that I've got in is only capable of reading 500 watts, so we have to be on the 500 watt scale. So a deflection to there is 100 watts. Now you'll see as we transmit, which I'm going to do now, and I'm talking to the microphone, as I'm using the speech there to talk into the microphone, it looks like as if the transmit power isn't making it very high level. It's, you know, if half that scale is 50 watts, which is probably around about this mark here, then it looks like we're doing way under 50 watts. But I can tell you we're not, which you'll see in a moment when I do a demonstration. It's just that the analog meter can't catch the fast changes in the amplitude as we're modulating the signal, because SSB is very efficient, and whenever there's no modulation, there's no power. It's only when we start to talk that we actually get RF power, and depending on the syllable rate of the speech, the frequency component of a speech, the harmonic content, the way the vocal cords modulate the carrier, will all depend on whether or not, you know, if a speech is constant, as in we have a tone, a constant tone, then we'll get a constant power. But if a speech is varying in amplitude, in frequency, in tonal quality, that will then reflect on the way that the meter can read RF power. But it doesn't mean for 1 minute that the transmitter is only doing this low level of power, which you'll see in a moment. So if I just talk into the microphone and make different sounds, you'll see the difference that it has on the RF power. 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. So you can see there, you see, as I'm modulating it. Now if I make another funny sound, oh, so you can see there that the tone itself, by changing its frequency, depends on the amplitude of the RF power. Now, even though we're just talking there naturally in speech, and it doesn't seem to be doing much RF power, if I just move the camera over to the ammeter on the power supply, you will see that it's varying quite a lot, the current meter. So as we're talking there, I mean, obviously we can see that the modulation there, the first mark on the top red scale there is 25 amps. So we're doing about 15 amps roughly there while I'm speaking peak. 4, 3, 2, 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. So you can see there's a lot of current being drawn. But yet, when we look at the RF power meter, 2, 2, 2, 2, 2. So again, we can see that correlates not necessarily to the current meter. As I'm talking there, as you can see, the RF power meter is hardly moving really. But yet, when we look at the current consumption there on the modulation that's having an effect on the current being drawn on the power supply, you can see a notable increase massively. And of course the RF carrier is literally jumping up and down to 100 watts peak as I'm talking there on the carrier or near that, and thus you know, the average power, if you like, if I can get the reflection off that meter, the average power on the RF meter isn't really reflecting that. So, as I say, there are methods of measuring SSB signals using, for example, a constant tone being fed into the transmitter, and that itself then would, you know, obviously, as the speech is propagating the carrier in amplitude, then it can measure that peak power very quickly and be able to naturally pull the transmit peak power out as a measurement. So by modulating a tone is the easiest way to get most RF meters to measure if they don't have a peak power hold capability on them, which a lot of test sets and quite high-end analog meters have. So that just gives you a little demonstration of that. I'm just going to have a go at tuning the VHF power amplifier section now with these two trimmer capacitors here, just to get maximum output power on CW mode on 145 point, I think it was 9 it wanted you to do the testing on. So I'll just see how much we can get out of it, and let's have a look here. 145.9 megahertz, I've got that on there. Right, we're connecting it back up to the Marconi, and I'll just get this screen set up, going now on there. Okay, right, so just put it to sort of 50 watts or thereabouts, and then just going to see if I can make an adjustment onto the transmitter. So we'll just try and adjust 46 watts, 47. Alright, so 47 watts there roughly, adjusting that trimmer. Can't get any more than that. 46.88 on that, and it should be doing 50 watts. I think we'll peak it roughly, yeah, it's about there, I'd say. 46.45 watts. Right, just get it up to 100 watts on CW and see what it's doing there. There, 98 watts. That's better. Get it down to 10 watts. See what it's doing there. That's doing 10 watts now. VHF. And then for 5 watts there on there. So that was just adjusting these capacitors here, TC1 and 101 and 102, which are these two capacitors. So that's improved things there as per the manual as well. Right, I think we've just about done. We know the UHF side's working because we established that right at the beginning, so I don't need to do any measurements with that yet. I think we'll whip the case on and reassemble it all, and then I think do a last review, and then I think we're done. Okay, I've just been looking at the service manual, which we're going to look at now, regarding the alignment mode for this particular radio, and it looks as if, from what I can see here in the manual, there's an alignment mode that you can go into by pressing 2 buttons down and powering it on. Puts you into some kind of adjustment mode, and then within that there's like a menu number, which then appertains to this table, and there's I think up to 124 adjustable DAC values that you can change. So there's this table, and then there's these two tables here right up to 124. Now the menu tables that are further down as well in this section of the manual refer to what table you should be in for measuring the TX power you know, obviously for the transmitter side of things as well. And again here in this section, power for the POC, power meter, as well as the physical output power that the radio will do on all the different frequency bands. Anyway, I've looked into this, done a bit more research on it off camera regarding this adjustment procedure, and I've read some quite disturbing articles about it, where there are people that have bricked the radio purely by trying to do this loading of the firmware onto the radio, which I'm surprised at really, because most PMR radios that Kenwood manufacture, and I have plenty of them here, they do have the alignment software, or the firmware at least, in the radio. And being private mobile radio, commercial radios, you can adjust the alignment parameters on them, and there's no additional software that needs downloading to them other than that. You know, the fact that the programming software allows you to talk to the radio, and they've even got manual tuning modes on them as well, a service mode, just like this radio does. But you don't have to pre-download any firmware on them in order to get into that alignment mode, whereas here you do have to set the user firmware. You have to program it with that, and there's a slide switch on the microprocessor board you have to set in a particular position. Then you have to connect an old school RS232 serial cable up to the PC, and then using the Kenwood firmware programmer you would then program the radio with the user firmware adjustment software, and that then would allow you to get into this menu, which is here, and then manipulate the table and alter the DAC values for each parameter. Now, the issue is, of course, that I've read on the internet, is that I think most people got modern PCs that got USBs, and having to use USB to RS232 converters, is the fact that back in the, you know, early 2000s, a lot of machines back then they didn't run at great processor speeds, and naturally when you're programming, as you'll see on my Motorola programming videos and other things that you'll see on my channel, when you're using the older software with older computers, the slower the clock speeds on the UART controllers for the RS232C outputs, the microprocessors running slower, the serial buses running slower, everything's running slower. And of course the software is written, coded in such a way where when it's transferring firmware data from the computer to the radio, it's doing it at a particular speed for the handshake to occur, you know, the ACK and the NAC responses from the radio. And so if things are running way faster than that, like on modern machines, which it's reported on the internet that people that are using, you know, really fast modern PCs to program these older 20-year-old radios, results in a total corruption of the firmware. And the problem with this firmware programming, from what I've read, is that if it bombs out halfway through doing the programming, it'll brick the radio and it's unrecoverable. And obviously these radios are quite old, they're 20 plus years old, so the chances of being able to get Kenwood to repair or put right the firmware in the radio once it's been bricked without major cost, or even not being able to do it, would be quite serious. So we can have a look on this radio anyway to see how you get into the alignment mode, and whether the previous user of this radio has downloaded the alignment software. If that's the case, then winner winner chicken dinner. But as far as I can see, I don't think we're going to be able to get further than that. Just getting into the menu, I doubt the previous user to this has done that. But at least you can see the procedure. So to get into the alignment mode, it says here you've got to hold down the NR key, the noise reduction key, and the mic car key, and press the power button. Adjustment mode is set by the menu number is displayed, set and the menu number is displayed below the memory channel on the main band left side. So, and then it says to select adjustment mode menu number, turn the multi-channel knob to change the menu number, change the adjustment mode setting using your plus and minus keys, probably on the microphone, and then it says write adjustment data, plus and minus key on the main unit, or up down key on the microphone. So menu, alright, on menu number 124. So menu number 124 is EEPROM right, which is this here, EEPROM right. So when you select that, then you'll be able to store any data that's been previously set in any other part of the DAC settings. So let's have a look at the radio then and see how we do that. So the NR key is, well, that's the MR, so that's not it, that's NR, noise, there we are, noise reduction, and the mic car key, where's that then? There, look, there we are, mic car key. So it's that and that, those two together, followed by the power button. So it's that and that, followed by the power button. So presumably turn it off, press and hold those two down. Oh, now then, that's going to be interesting. Can I do it? Oh yeah. And then press the power button, keeping those two buttons down. Ah, here we are, adjust OK prog. Right, so menu number 25 it's on at the moment. Now it says the multi-channel knob will adjust that menu item, so that is the multi-channel knob there. Ah, right. Oh, well, it's not adjusting that. It's not that knob, is it now? That knob? None of them knobs. This is a... No, it's not that. What about the up down button there? It's not that. Microphone up and down button. No, I can't get that menu. So it's not had the firmware. If it had had the firmware, adjustment firmware downloaded to it, it would mean that right now we'd just turn this and it'd be going up and down that menu button with the look of it. I don't think I've misread it. It does say there that when the adjustment software is loaded and the main unit is turned on, a beep sounds to indicate the adjustment mode. This does not indicate a failure. When any key except PTT key is pressed after frequency is displayed, the beep stops. Do not return the TS2000 that contains adjustment firmware to the user. So it looks like as if we can't go any further then with that, because there's no firmware adjusted. Procedure for writing adjustment firmware for both user and adjustment firmware. Right, I see. Adjustment mode. It says the TS2000X can be adjusted manually by tuning a coil, trimmer, etc. Or by setting the service adjustment mode. Adjustment with panel keys. In the service adjustment mode, simply referred to as the adjustment mode below, adjustment items are shown in the menu number 00 to 126, and all data are saved in the EEPROM IC7. To enter adjustment mode, the user firmware in the main unit must be rewritten with adjustment firmware. The user firmware is factory set RC. Right, so that explains it. And there's a procedure there, look, about it, which talks about the flow diagram, which goes into detail about that. So it's a shame that, because we're looking forward to trying to do some adjustments, but I don't want to take the risk of trying to program the radio with firmware only for it to get bricked because it bombs out halfway through. I do have a very old Intel Pentium 1, I think it is, compact machine here that I could potentially use, but I think it's a bit too risky, and as you know, if it ain't broke, don't fix it. But it's a shame that, because they stopped you effectively from getting to the alignment menu. I don't know why they have done it as they have. Oh, and I've just noticed something as well. That 125, it displays checksum, and when you look at the display, I thought it just said 25, but it isn't. If you look carefully, there's a little 1 just before the 25, so to be careful with that, because that looked like it was just 25, but it's actually 125. So that correlates with the obviously the checksum, which is here. So, and there we have the reference to it there, 125 checksum. So that is what it's displaying now. So it's stuck at the checksum bit, so it doesn't have the rest of these menu items, you see. So what a shame, eh? What a shame, but not to worry. Such is life. So we can't get it out of that. It just goes to like some kind of a lockout mode, or you know, display test mode, and that's all you can do. So there's nothing else we can do with that, I'm afraid, for the alignment side, apart from what we've just done with the TXPA for the VHF and similar, where we've adjusted it manually. But yeah, such a shame, but that's the way Ken would want it. But had it been an ultra modern radio, obviously that it'd be worth doing that perhaps, but I'm certainly not going to be doing it on a 20-year-old radio that could get bricked by, you know. That's certainly what a lot of people I've read about the internet purport to have had with them, is the fact that, you know, they have this issue where the radio gets corrupted halfway through programming it. It just bombs out. So probably get some communication failure. It's probably shoving data to the radio too quick for the radio to respond back to the machine, the PC, and then it gets to the end where it does its checksum or whatever, or halfway through, and it just drops it. So I'm certainly not going to risk that, and I wouldn't have thought you would either. So at least you've seen that section of it anyway. Okay, so this is the final part of the video now. I think we've just about come to the end here. We've got the lid back on, it's all nicely put back together, all fully functional and working, as we've done with the testing. I think we've done a good repair on this. I mean, obviously it had a major fault on it, where basically 90% of the radio's frequency bands didn't work on transmit. Fortunately in our case it wasn't a severe fault, you know, where we'd had a burnout of components on the board which had damaged the PCB, which sometimes happens. We didn't get anything really standing out at ourselves with the fault as such. There was no physical damage or evidence that something had blown, other than the fuse had gone, obviously, and we managed to get another fuse and replaced that, and then we found that there was a faulty transistor after doing testing of transistors. And there's various ways of finding faults like that. Obviously you can probe around using a spectrum analyzer, but again you've got to be really careful with some test gear, especially when you're dealing with RF powers like this radio can produce. You know, you've got to be so careful, because even the drivers and the pre-driver stages are kicking out about 10 to 15, possibly 20 watts in some cases, to get the RF final amplifiers to produce 100 watts output. So spectrum analyzers, you know, typically have a maximum rating up to about plus 33 dBm, which is 1 watt. So, you know, you're talking damage to a spectrum analyzer. There are other things, like I've got diode probes as well. I have one here somewhere, if I can find it. They're quite useful for measuring RF levels on circuits, particularly RF power amplifiers that are in the low to medium power ranges. You can make one yourself, a diode probe, using an OA91 diode, a 1 nanofarad capacitor inductive choke, and then feed that off to a voltmeter or an oscilloscope, and you can probe around sort of, you know, there's quite common designs for RF probes. There are professional versions of it, which I've got floating around here, but they tend to be low power levels, you know, we're talking millivolt levels maximum, so that they're okay for circuits that are in the milliwatt range. But when you get into, you know, tens of watts, it overloads them, it can burn them out, and not very good, the commercial RF probes. But the homemade ones, you know, you can make yourself an RF probe. One of the things that you've always got to bear in mind as well when you're probing round on the circuits is that the impedances as well change. You know, you can't sort of expect huge amounts of RF power or gain across some transistors, depending on how they're matched on the input and output. Like on the HF side, we've got those transformers. Well, they're not you know, going to be in the 50 ohm region, you know, because obviously the balance, and they're effectively matching a push-pull stage to another amplifier whose impedance needs matching through matching networks. So if you go sticking a 50 ohm RF power meter across in series with a 1N capacitor, for example, you will get some indication of some gain, but you're not going to get absolute figures. So if you think that, you know, you're looking for absolute RF levels, you're not going to get that. You're going to get a rough indication that there's something there, but it ain't going to be exact. So I think for the difference in impedances, the best way I've found to test around some of the transistors regarding the RF conditions is to use a diode probe, in which case that way it gives you an indication that there's some RF gain between the base and collector, for example, on the input and output of a transformer or caps, things like that. You're not worried about DC levels as well, because obviously you've got a spectrum analyzer connected to a circuit. You know, you're going to introduce DC volts into a spectrum analyzer, which won't be received very well by the spectrum analyzer, to put it bluntly. And also there's a risk of overloading the RF front end, as I say, with the TX power. So best staying away from sensitive, expensive instruments for testing round that circuit. You can loosely couple a bit of coax with a little loop at the end, as long as the inner conductor's, you know, insulated, it's not exposed, and you can sort of touch round and sniff around the board. But, you know, just for an indication with the spectrum analyzer, that's possible. So there's lots of little things you can do, you know, but it's just being careful not to damage a very expensive spectrum analyzer when you could have done the same checks using something far less expensive, such as a diode probe. Now, I've got one here. I've just laid my eyes on it, would you believe? And I have it here, made by Raycall Instruments, and quite big in RF probes. So we've got one here. This is ex-Ministry of Defence, and again, Raycall manual. This is for a particular instrument, but it's still quite useful. But the general principle is still there. You can make your own diode probe out of, as I say, an OA91, you know, diode and cap, etc. Even a Schottky diode that's for RF would be more than adequate. But again, have a look at this. Is an active probe, is this, and so in here is our active probe unit. So this is a typical thing that you'd have. So that would connect off to your, you know, your oscilloscope, etc. And then this is the actual probe. But as you can see, it's a little bit impractical, really, because you've got all these different attachments and things that go on the end, like that, for example. So you get the RF ground as well as the actual pin for touching on something. But again, in a radio this sort of size, that's impractical. So I tend to have these little ones that are made up from like old pen shells and things, where I just have like a little prong sticking out the end. There's an OA91, a 1N cap, an RFC, and then radio frequency choke in a ferrite bead, and then I've got a coaxial cable going off with a BNC at the end to go and do that. I've got it in here somewhere. If I find it, I'll show it. But it's very similar to that, but it's just a miniature version, whereas this is more of an expert RF probe, which has obviously got its own power and what have you. But this is only good up to just basically a low frequency range. Great for HF, but it is actually only good, I think, up to, is that 20 volts or something RMS, up to 1 megahertz or something. So, or 3 volt RMS at 150 megahertz. So basically, you know, there's a damage overload there, these are the levels that you can damage it with. So if you've got a 10-watt power amplifier and you're probing round on it, it'd be easy to damage that. So there are diode probes and there are diode probes, and so, you know, you're best off really, if I were you, making your own. And that way then you know you're on a winner. But yeah, interesting little repair. I mean, obviously interesting faults. In this case it was that 2SC 1972 transistor. I think that was it there, the offending article. Again, no big hole in the middle of it. It was sinking a load of current permanently, and it was difficult to find, you know, because normally these smoulder, char, they have a big crater in the middle, and you sometimes find part of the transistor floating around inside and it's burned the board or that kind of thing. So we're quite lucky in our case that didn't happen, but it was just the integral diode within that that protects it. A lot of flyback transformer switching transistors that are used in like CRT TVs or in switch mode power supplies, for example, have the integral diode in to protect back EMF from blowing the junctions in the transistor when it's switching at high frequency, and thus inducing a high voltage across the coil it's switching. So this particular RF transistor has an integral diode as well, and that had obviously gone short in this case, and then it was or near short and sinking a load of current, so it was acting as a resistor. So there are so many different things, you know, that can occur with these fault conditions. Some are easy to spot, some are hard to spot. So yeah, that's a pretty good little repair. Pleased that we've got the radio going. Didn't spend much on the spare parts. I was quite lucky that the RF transistors that I managed to get off eBay were reasonably cheap, and they were from a good source, where so many, or you know, can be counterfeits. We use the transistor tester, the fluke meter as well, to test the transistor junctions and fault find down to component level that way, and then carry out an effective repair. So with that, I hope you've enjoyed the video. If you like the video, please consider subscribing to the channel. It helps with the viewing figures, and there'll be more repairs like this coming along as well, and more test gear and radio equipment to repair and have a look at, so keep it interesting. And thank you very much for watching, and we'll see you again in the next one. Thank you. Bye bye.